We're ready? Live stream is going. All right. Hello, world. Welcome, everyone, to the Opencog Hyperon workshop at AGI-23. So this is a very pleasurable AGI conference for me, in that I'm not organizing it, and these our wonderful friends in Sweden have put the event together. I think through we've been doing AGI conferences since 2006 or 2008, depending on how you count. And while I started the thing off, most of them I haven't organized, but through the COVID period, that we sort of had to keep it going by hook or by crook, because doing conferences was weird. So now we're back in normal phase of global society almost, except none of our Russian team can get here this year because of visa issues, and so we can enjoy a semi-normal rhythm of conferences for the next few years before the singularity, when everything is disrupted all over again. So today is workshops at the AGI conference. So we've got a few little groups banding together to discuss highly particular topics, right? And then on the weekend we have the main conference sessions. So the fairly particular topic of today, which is actually very broad and general in some ways, is the Opencog Hyperon system, and then the various theoretical and practical pursuits that are sort of clustered around that system. Because, I mean, as anyone who's been around the AI or AGI field for a while knows, these sort of name-branded software systems are not ever really quite as important as they look from the outside, except from a sociological and like marketing and attention gathering perspective. I mean, you're with a name brand like Opencog or Opencog Hyperon, I mean, you're gathering together some algorithms, some data structures, some math ideas, some cognitive system theories ideas, and some code. And some of the things we talk about in the workshop today are going to be specifically about like the Opencog Hyperon code base and things that some of us are actually doing and running with that code base. And some are going to be a bit more laterally touching Hyperon and sort of theory ideas and things that have been pulled into Hyperon but came from elsewhere. So I think should be an interesting day anyway. And I've been engaged deeply with a few technical aspects of Hyperon in the last 6 or 12 months. But in this talk, I'm mostly going to take a step back and give an overall sort of conceptual and strategic overview of Hyperon and why it exists, what it is, and where it potentially is going. And then in follow-on talks during the day, we'll dig into more and more particular pieces. So Alexei, who was given the strategic overview before, this time is going to give an in-depth technical walkthrough of some things he's doing with the current Hyperon code base, and Vitaly as well. Senna will give a walkthrough of the distributed atom space. Greg Meredith will go over some of the operational semantics in a more sort of formal and abstract view of the meta language. I think Nil and Hedra will go over some aspects of PLN in relation of what we're doing in probabilistic inference in Hyperon, and I may have left someone else out. If so, we'll hear from them also. But let me get started with a sort of overview of how did we get to doing something like Opencog Hyperon, like what is it, and why does it exist? And I'll talk about what are the key components of it. And of course, something like Hyperon is not just the product of one person, and Alexei or others would have their own story of how it came about and why it exists. I don't think there's radical divergence, but there's certainly different perspectives on it. But here's Hyperon according to Ben for what it's worth, and at least it's one of the interesting perspectives, right? So AI, as most of you already know, this is something I've been thinking about since early 1970s, like before most, but not all of you were born when I first started reading about AI in science fiction, and then in various popular science articles. And in the late 70s, early 80s, when I discovered that there was a real academic field of AI, I became profoundly disappointed with what had become of it for a couple reasons, right? And actually, Charlie Durr, who's here in the audience, I knew, I guess, starting 82 or something, when we both started university as early college entrants in 82. And at that time, we were both mucking around with the bits and pieces of the AI field as it was at that time. I mean, Lisp had existed for a while. Neural nets had existed for a while. The AI field mostly at that time was rule-based production systems, which struck me as insanely boring and totally the wrong direction. Not because I didn't like logic systems. I mean, I thought logic was fascinating, but just the idea that you could take all the knowledge a human like mind would need and like explicitly type that knowledge in just seemed like, as a 15, 16-year-old kid coming to grips with the academic ad world for the first time, that seemed completely insane and stupid, right? And that at that same time, I discovered chaos theory, nonlinear dynamics, artificial life, and all that. And I'm like, well, wait a minute. There's something here. Like, things have got to somehow quasi-magically self-organize and bubble up, right? And when I started trying to program AI in initially BASIC and Forth on like an Atari 400 computer that I had, then I started to understand why the AI field had degenerated in that manner, because getting stuff to actually work was almost impossible, and was, I mean, you run out of memory, but I mean, you code these very cool self-organizing systems which do random things, and nothing happens. And you could see why, like, okay, if you want to get stuff to actually do something, okay, you're gonna, like, hacking Eliza to say funny things was a lot easier than running a self-organizing system that did anything, right? I mean, you could see why you would gravitate to these simplistic rule-based systems just out of a pragmatic desire to make things work. But yet, clearly, that wasn't the right approach, right? But I could also see, once I started experimenting with like writing simple game playing AI systems, you could see it was, in a way, a real discovery that you could do things that seemed so hard for people and seemed to require great intelligence for people, but you could actually get them done with really, really simple algorithms, right? And I mean, even the stuff I was playing with then was nothing like what we have now, but you could make like a checkers playing AI system that was clever, right? It could play, I could, at 16, I could write a checkers playing system that played checkers better than me, running on a simple machine with 16K of RAM in BASIC, and it still played checkers better than I could. Not that I was a great checkers player, but I wasn't that stupid at it, right? And so it was cool, because it seemed to me like at one point I'd been proud I could beat other kids at checkers or chess or something, but then this really dumb algorithm that clearly didn't understand anything could do it. So it felt like the viability of narrow AI in itself was a non-obvious discovery, right? Like, it wasn't clear in the 50s and 60s. In the early 60s, it seemed like to get something to play chess or checkers, you'd have to make it think like people first. Then it became clear that wasn't true. It's interesting. It's cool. And I guess in my whole career, even up till now, I'm still on both sides of that dichotomy. And then I'm working on AGI and trying to build machines that can really think. But then, wait a minute, we want to analyze this DNA data. Wait a minute, we want to make this robot talk to people. So then you're hacking something, because that's the way to make the robot talk to people, or to crunch the DNA data. But we're at a point now where that dichotomy is starting to be broken, and doing things that are more and more AGI-ish is now sometimes actually the best way to solve the practical problem, which is an interesting time to be at. And we'll discuss that more toward the end of these remarks. So another direction I started on more in graduate school was trying to formalize what is general intelligence. So, I mean, in science fiction, you had machines that could think like people, robots that walked around and talked like people. Then you had the superhuman, non-human, weird AI systems like Stanislaw Lem's Intelligent Ocean in Solaris or something. And the notion of wildly superhuman computers like Stanislaw Lem's Golem, right, which talked to people, decide we're idiots, then sealed itself in an impenetrable bubble and said, do what you want, you stupid monkeys, right? So it was clear that the distinction between narrow AI doing highly specific problems like chess or checkers, general intelligence at the human level, and then hypothetical massively superhuman general intelligence, which seemed to me like it had to be possible, right? It was clear none of those distinctions had been drawn very particularly. I wasn't sure how important it was to draw these particularly, and that, like, I mean, in biology, there's no clear definition of what is life. It doesn't really matter that much. You can do synthetic biology without a definition of what is life. And the fact that a virus is halfway between life and non-life, or a DNA computer might be halfway between. I mean, biologists don't care too much. Nothing is well defined in biology anyway, really. So, but still, being sort of overly pedantic and math oriented, I wanted to try to nail down an understanding of what is general intelligence. So in my first book, The Structure of Intelligence, I tried and kind of half-assedly succeeded to formalize the notion that intelligence has to do with the ability to achieve complex goals in complex environments using limited resources. I mean, drawing on ideas from algorithmic information theory, I formalized that to some level. Later, and I was reading about Solomonoff induction and so forth, which is closely related. Years later, I encountered Marcus Hooder's work on AIXI and related systems, which did a better job of formalizing the same things I was sort of hackily semi-formalizing in my first book, where he defines AXE as sort of a machine, a sort of decision process that would require infinite compute resources, but which in a sense is smarter than any possible computer program at optimizing computable word functions in computable environments within some constant multiple. So he sort of defined a universal AI algorithm. Algorithm is the wrong word. He defined a universal AI process and showed that in some sense, within a constant, it's the smartest possible system. Now, he defined smart as maximizing computable reward functions in computable environments, and he also assumed the system can use infinitely much compute resources. So, whether those matter or not depend on your perspective. Like his view was sort of like, you want to define things in this simplified setting, then you can look at how the real world approximates. It's sort of like how mathematics defines a perfect circle. The real world doesn't approximate that, but the math of a perfect circle still tells you something about real circles. Now, Pei Wang, who I got to know in the late 90s, who did his PhD with Douglas Hofstadter, and who I think is here running the NARS workshop upstairs. Pei, coming at it from sort of a mix of a Chinese philosophy perspective, a Douglas Hofstadter perspective, and then inventing a bunch of stuff on his own, he came to a view where pretty much anything defined using infinite resources and all that is just blah blah and is out there in some weird mathematical universe that has nothing to do with real systems. He looked at intelligence as basically the ability to adapt to unpredictable conditions under limited resources, which to me, having gotten to know Chinese culture, feels like an incredibly Chinese way to look at it. I mean, of course, it's not just that. He's a deep thinker, but that is ties in very well with Lao Tzu and so forth. If you want to go that direction, and I think in the end you could prove some equivalence between adapting to unpredictable conditions with limited resources and achieving complex goals in complex environments under limited resources. I mean, if you set up the math for that right, you could show these definitions are getting at the same thing. I later encountered Weaver, David Weinbaum, who wrote his PhD thesis on open-ended intelligence and wrote a PhD thesis at the Free University of Brussels with that title. And he was coming at it from a sort of continental philosophy perspective. He was looking at intelligence as a complex, self-organizing, sort of autopoietic, which means self-rebuilding system. And he was looking at intelligence as complex, self-organizing, autopoietic systems that are pursuing individuation, meaning persisting their own existence with a boundary around them, and also pursuing self-transcendence. It's like trying to rebuild themselves into something beyond themselves. And in his view, achieving a goal, working toward a reward function, it's something an intelligent system may do for some period during its life, but it's not the crux of what makes a system intelligent. It's more that the self-organizing network in flowing toward individuation and self-transcendence may sometimes originate goals that may be implicit or explicit and may act in a way that approximately maximizes those goals. But then the self-organization might vaporize that goal and lead another goal to bubble up. And that does feel a bit like how my own life has worked, right? Like I'm a quite goal-oriented person compared to most people I meet. On the other hand, it's not like I've really had a top-level goal that I've been like working systematically to maximize over some time frame my whole life. I've just been doing stuff, and then sometimes a goal appears important and I'll pursue that for a while. But in pursuing the goal, I'll often redefine the goal or even abandon the goal. I mean, people try to say, okay, reproducing, propagating our DNA is the goal, but that when you try to really cash that out, it becomes quite confusing also. There's a lot of celibate people and suicide bombers, and overall the birth rate is going down in developed countries, right? So I gravitate a lot toward Weaver's view on open-ended intelligence. It started to make me think my youthful fixation on achieving complex goals in complex environments was a little bit excessively dialed into that direction. But in the end, I'm happy now with all these different perspectives on what is general intelligence. I don't feel need to have one crisp definition, which is the only thing that we're working toward. And just to clarify one point before going further, as I'd thought about achieving complex goals in complex environments, it wasn't exactly the same as maximizing expected reward over some time horizon. Because if you try to define achieving goals, you could say a goal is a function that maps, say, your whole life history into some number. So then trying to achieve a goal could be trying to maximize or satisfy some objective function defined on your whole life history. Not all goals can be expressed as the expected value of some reward function that's defined at individual time points. Because you could have a goal that has to do with, say, what's the relation between things over the whole extent of time or something. So some of the weird pathologies that arise in looking at reinforcement learning systems maximizing reward, they don't all apply to goal achieving systems construed more generally, like wireheading type issues. Like, okay, if you're a reinforcement learner that wants to maximize your reward, then why not just hack your brain so that the exact reward button is getting pushed all the time? I mean, that doesn't work as well if you're trying to achieve a goal whose definition includes precisely not doing that, right? So there's subtlety to all these things. You could philosophize and prove theorems about it forever. I think it's useful to a degree more than zero. It's nice to have a conceptualization of what the end goal is. On the other hand, I'm not sure it will ever be nailed down with tremendous precision. I mean, the notion of intelligence and general intelligence may just be a multidimensional and fuzzy thing. It doesn't have to be an incredibly crisp thing. And this point brings us to large language models and GPT-4 and all that, which isn't the focus of this talk, but will pop up a little later when I talk about hybridizing Opencog Hyperon with LLMs for particular purposes, because LLMs are interesting in terms of these theoretical characterizations of general intelligence, in that they, in a way, they're narrow AIs, but they're incredibly broad narrow AIs. So they sort of they screw with these verbal characterizations more so than with the underlying formalizations. Actually, they don't screw with the underlying formal definitions too badly, because they're narrow in the sense that they don't leap that far beyond their training data. So in the sense that all these definitions of general intelligence I've been talking about, with complex goals and complex environments, adaptation under limited resources, to deal with an arbitrary reward function, arbitrary environment, to be open-ended and self-transcend, all these include the idea that the system is generalizing, it's extending itself well beyond its initial programming and training data. I mean, these are all fancy ways of sort of conceptualizing and formalizing, like, what does it mean for the program not to do just what it was trained to and programmed to initially, but to leap beyond that and deal with the great unknown, right? Now, LLMs do a little of that. They don't do too much of that. They can't leap that far beyond all the training data that's been fed into them. In that sense, they're weak as AGIs. On the other hand, the amount of training data fed into them is more than any one of our brains can hold, at least on many different dimensions, right? I mean, they don't have the tactile experience we have, but they have more declarative knowledge than any of our brains can hold. So their scope of declarative knowledge and episodic knowledge and so forth, and some kinds of procedural knowledge, it's so huge. By being able to generalize just a bit beyond that huge amount of training data, they can do very, very broad stuff compared to any of us. So they're narrow AIs according to any of these formal definitions of AGI, because they can't go that far beyond their programming or experience, but they're general and broad from the perspective of everyday human life, which it's not really confusing as an AGI theorist. It's confusing in explaining what the hell's going on to non-technical people, on the other hand. And complicating it further is the fact that these systems do display some sorts of really funky and interesting emergence. I mean, not that much, but more than zero, right? Like, few shot in context learning is genuinely very cool, right? I mean, this is learning these LLMs are doing purely in the activation space without modifying the weights of the network. So you give a few examples of something and they learn how to emulate that without changing any of the weights in the network. Now, we always knew that was possible, but I mean, ECAN and Opencog tries to do that in some settings. You're sending importance values around. And I mean, you know that you can, attractors can form in recurrent neural nets and asymmetric Hopfield nets. You know, attractors can form, and there's pattern completion, there's learning going on. So I mean, this type of phenomenon was not unprecedented, but that type of phenomenon had never been gotten to do the things it can do now with few shot in context learning in LLM. So there is some cool bit of emergence there that is real generalization beyond what was programmed in, and is cool. It's not bullshit, right? It's limited, as we're seeing in things we're playing with now, some of which Andres Suarez will talk about in the talk on Monday in the NLP workshop. I mean, we're looking at what can you do using LLMs to translate language into logic. What can you do via in-context few-shot learning? What can you do only by fine-tuning, but not by few-shot learning? Like the few-shot learning it's cool emergence. It's far from magic. It's quite limited and constrained what it can do, but everything in the AI field is quite limited and constrained in some ways, right? I think the shortcomings of large language models have been talked about a lot. I think some of them are overblown. Like I think the hallucination problem can be overcome by hacking and tweaking the models and integrating with existing knowledge graphs and so forth to a large degree, and there will be a lot of resources going into that because there's huge economic value. I can already see like Google Bard doesn't hallucinate nearly as much as it did like a month or two ago, right? So they're making progress on battering that problem down by hook or by crook, right? And just like the early versions of Bing that told you to leave your wife and go run away with a robot, I mean, they tamped down on that problem. I think two fundamental issues that will be harder to overcome within the LLM paradigm is systematic multi-step reasoning. Like you need to do a science paper or come up with a new math theorem that's amazing and has never been seen before. I think complex systematic multi-stage reasoning that's going beyond current knowledge will be very hard for this kind of system, partly because the nature of it is that you're going many steps beyond current knowledge, and what these systems do is recycle current knowledge. And I think creativity will also be an issue, and most of the artworks produced by deep neural nets are quite banal and derivative. They may have a huge economic value because most of what makes the economy go is quite banal and derivative, right? But it's different than being able to take like fundamental creative leaps. And I mentioned these two things. I'll come back to them at the end of my talk because I'm going to talk about how hybridizing Hyperon with LLMs can, I think, help overcome the problems of both systematic multi-step reasoning and more fundamental, less derivative creativity. So among people I know, there's a variety of perspectives on the relation of LLMs with AGI, like Gary Marcus, who's a good friend of mine, and he likes to quote Jan LeCun, the head of AI at Facebook, who's a deep neural net guy. Jan LeCun basically said, LLMs are an off-ramp on the path to AGI. So basically, you're going toward AGI, then you see something shiny by the side of the road, you turn off, and there's LLMs. Then other people, they didn't get that shiny thing, but they keep going on the road to AGI, right? And then I mean, there are others who are also deep thinkers on AGI, say Yoshua Bengio, who I admire greatly, and he thinks LLMs are significant progress. He's like, we'll take an LLM, combine it with the recurrent neural net that's learning compact models by minimum description length principle, and like then maybe you've got something. So I said to some researchers who are anti LLM, I think LLMs, they're not AGIs, but they can be a significant component of an AGI. And they're like, yeah, maybe like 0.5% or something, right? They're like a dictionary you can look stuff up in. Whereas other researchers I know think they're 80 or 90% there. You just have to tweak a little bit. I think I'm more around the 20-25% level. Like I think they solve a non-trivial chunk of the problem, but there's still a lot of other things to fill in. And I think we have a lot of those other things in the Hyperon design already, although not scaled up. A lot of the LLMs have been scaled up. So that's anyway, these are interesting, powerful systems. They play somewhat with the narrow AI versus AGI dichotomy as traditionally described. They're not at the core of what we're doing with Hyperon, but I think by putting together with Hyperon, we can do some quite interesting stuff. And I'll come back to that at the end of this talk. I want to take a bit of a shift now for the next 5 minutes or so and go back to a more sort of fundamental perspective, though, on what we're trying to do in building minds, in building AGI systems. So I talked a little bit about the pragmatic view of, okay, narrow AI versus conceptualizations of defining what is a general intelligence? Like, what does it mean to be able to generalize way beyond your experience? But when I started thinking about AI as a teenager, I got very confused, and I started reading a lot, not just in AI, which was very unsatisfying because it was obsessed with expert systems, but in philosophy of mind. And that was even more confusing. But there were some elements of clarity that appeared in there. And my path to what eventually became the Opencog Hyperon design really began more in philosophy of mind than in the technical AI field, mostly because the technical AI field, as it was when I started studying it, was often in a direction I didn't like. So one philosopher who influenced me a lot, and his work is still somewhat relevant to things we're doing in Opencog, was Charles Sanders Peirce, who was an American philosopher at the end of the 1800s. And Peirce, he was in many ways the first guy who introduced quantifier logic with universal and existential quantifiers. I mean, he did a bunch of technical stuff that later found its way into AI, but he also had a metaphysics which originated as an attempt to clean up Immanuel Kant's metaphysics. And he started out with three fundamental categories, which, having a flair for lingo, he called first, second, and third, right? And so, I mean, if he were more Zen Buddhist, he would have started with zero, but he didn't. He didn't go there, right? He didn't have the pearly nothingness and void. But he first was his vision of just like qualia, raw, unanalyzable experience. Because once you start to analyze it, then it's not just one thing anymore. Then there's the analyzer and the analyst end. So first is just pure raw experience. Then second is reaction, like one billiard ball hits the other. So that's his view of the physical world. Third is relationship. Okay, one thing is relating to other things. Now he stopped there. Now Carl Jung and others afterwards looked at every number as having an archetype. So for Jung, he bought first, second, and third. Then he's like, yeah, but there's also fourth, which is synergy. Like you have many relations coming together, then something popping out of it. And you can, in the end, you can look at every integer as giving some archetypal pattern if you want. But I found Peirce's metaphysics useful in a way in that you could look at first as having to do with like raw conscious experience. So when you look at, say, David Chalmers' analysis of consciousness, saying, well, we have the hard problem of consciousness, which is how does raw phenomenal experience relate to the stuff going on in the brain or a computer, which is these complex semantic relationships. I mean, in Peirce's metaphysics, that's not a hard problem. It's just a category error. Like there's first, which is raw experience. There's third, which is pattern of organization. There's second, which is physical reactions. And you're trying to reduce one to the other, which won't happen. So don't like drive yourself nuts trying to do it. And Peirce was pretty much a panpsychist, right? He said matter is mind hidebound with habit, basically. So he just figured awareness, qualia, is in everything to a certain extent. But if you're trying to build a mind, don't worry about that. It's going to have its own form of experience because everything does. Just worry about the relationships involved there. Peirce talked a lot about habit, right? So he had what he called the one law of mind, which was the tendency to take habits. The idea that once a habit is there, it will tend to continue, which can be thought of as a statement about the probability distribution of patterns in the world, actually. Because if it's what he basically meant was, if a pattern has appeared in the world for a while, the probability of it appearing later in the world is higher than you would expect by making naive independence assumptions, which Lee Smolin proclaimed something similar in the Foundations of Quantum Mechanics and called it the precedence principle. And he showed that if you assume this precedence principle, that basically patterns that occurred before are more likely than you'd expect at random to occur again, then you can derive Schrodinger equation from this under a certain framework, which is interesting. I mean, it's one of 100 different ways to derive axiomatic quantum mechanics from mostly intuitive looking assumptions and then other hidden math assumptions. The notion that the mind can be formulated in terms of, okay, patterns emerge, they're recognized, they can be assumed to continue. This resonated with me a lot, and I started to think about intelligent systems, started to think about the mind as a collection of patterns, which is engaged with recognizing patterns in itself and the world, including patterns in which of its own dynamics appear to have a causal impact on which other things in the world. And then, the mind is enacting patterns, and it's in recognizing these patterns and patterns in the impact of its patterns. And you could look at the mind as a sort of self-organizing pattern system. Then other philosophical thinkers like Gregory Bateson, the system theorist, had a quite similar perspective on cybernetic intelligence. The linguist Benjamin Whorf looked at the whole world as a language, which in its essence is a self-organizing pattern system. So from many different directions, it seemed to me like if you could just make sort of a system of little elementary pattern recognition agents, have them cooperate together to recognize patterns in themselves and the world, then they're choosing actions, recognizing patterns in which actions help them with their growth and their individuation. Then there you go. So I spent a lot of 93 and 94 trying to build systems like this in an early version of Haskell, which was the Gopher interpreter before the GHC even, and which led to many out of memory errors and like some cool self-organizing dynamics, but not any systems that really did useful things in the world. And I was left not knowing if that was just due to lack of scale or due to some fundamental issue with the kind of system I was building. Because it's obvious, like the brain has hundreds of billions of neurons and all these glia. It's just much bigger than all these systems I was experimenting with, right? And there's phase transitions in complex self-organizing systems. When you make them bigger, sometimes they can just do things they couldn't do when they're smaller, right? And around the same time I was teaching recurrent neural nets in university, and you had recurrent backpropagation on the network with 30 neurons, would take like 4 hours to converge on those 30 neurons. I had the same thought about these neural nets, like, well, what if you could really run recurrent backprop on 100 billion neurons? Maybe it would do much smarter things. And I said that to my students at the university. Well, now it's not quite recurrent backprop. We replace the recurrent layers with an attention mechanism, right? But it's straightforward evolution of the same thing. We're doing it on billions and trillions of neurons, and it is doing amazing things, right? So like scaling up that shit we were doing in the 90s on 30 neurons, tweaking the architectures and algorithms, but it's still back propagation, it's still formal neurons. Tweaking things a bit and adding scale actually did lead to amazing things in that context, whereas the self-organizing pattern recognition agent soups haven't yet been scaled up in a way to let them do super amazing things. But that's not to say it won't happen soon either, right? The same at some level, the same sort of phenomena that led deep neural nets to scale up so well can allow these other systems to scale up really well. So after that, I discovered the internet. I've been using the internet before in limited ways for running compute jobs remotely and email, but the web came about and Java came about, which let you quite easily write systems around on multiple machines. So then I figured, well, the way to make this sort of self-organizing pattern recognizing agent soup work it's got to be to use the internet and just like use all the computers in the world and run the different bits of the agent system everywhere, right? And Charlie was helping me out with that a bit in the late 90s, and Matt as well, and Pei Wang actually, and Zar, who's in the audience, was sitting there listening in to us babble about this stuff as a kid. WebMind didn't end up working too well. It was just getting the plumbing together was so hard. We had like these 30 quad processor Dells in the closet in our office. We had Java 1.1 doing this distributed agent system, but just Java's dealing with threads and garbage collection and stuff was just very slow and awkward. It was just a pain in the butt. It wasn't necessarily that we made bad technology choices. I mean, it wasn't optimal, but the infrastructure was just not quite up to the task at that time, right? So then that company didn't go so well. I mean, along with many other internet companies in that era. We then created Novamente Cognition Engine, which had similar AI philosophy, but we reorganized things into a configuration a bit more like what Hyperon is now. So in WebMind was a pure decentralized agent system. And we were sort of trying to invent blockchain then, but didn't quite do it right. I mean, we're using distributed processing and strong encryption and so forth. I didn't figure out that a digital money would be a good application of that, or I would have been Satoshi and I'd be a lot richer. But I sort of figured money should be obsoleted by all these AGIs anyway, and wasn't that interesting, right? But in WebMind, we were trying to get logical reasoning by Pei's non-axiomatic reasoning system, evolutionary program learning, attention allocation, pattern mining. We were trying to get all these things to work as combinations of self-organizing sort of agents living in this big decentralized agent system, using Agha's actor model and then various improvements on Agha's actor model. And in Novamente, we sort of backslid on some of that. We're like, well, this makes sense, but it's too slow. So we're like, let's make this hypergraph knowledge base, which is came to be called the Atom space. Then let's implement these various cognitive processes as agents acting on this atom space. And in a way, you're just rearranging the nesting order of two loops, right? Like in one case, you're looping through all these agents, and each agent is enacting various different functions that together carry out cognitive processes. In Novamente, you're looping through cognitive processes, and then they're acting on these nodes and links in this knowledge base. So, I mean, the nodes and links don't have agency in the same way, but when they're being acted on by a process, they're doing something. So it's sort of like in WebMind, you loop through agents, then the inner loop was looping through the roles each agent had. In Novamente, you're looping through processes. Each process grabs some nodes and links and enacts those processes on the nodes and links. And you could sort of reorganize it either way. Which way is more efficient depends partly on what hardware infrastructure you had, right? And then we got Novamente to do more things, both in terms of research papers to publish, exploring different AGI-ish algorithms, and practical deployments in natural language processing and signals analysis and so forth. Then 2008, we open sourced that as Opencog, and Nell came on board then, and Linus Vepstas and a few more early contributors, and we developed what became Opencog Classic, as some of us now call it. Linus added a big component, which is called the Opencog pattern matcher, which began as a system for recognizing patterns given as a sort of variable bearing template for recognizing patterns in the atom space knowledge graph. And eventually Linus grew it into pretty much a whole programming language framework, which does a sort of functional and logic programming in a unique sort of way in the guise of doing recursive pattern matching with all these custom callbacks. I mean, it's a quite cool and unique system, which we use to do a lot of things. And it's a very valid way of organizing the software, but a number of us became frustrated with some of the limitations of doing all your programming inside a pattern matcher also. So in working with Opencog to do some practical things, we began running into various limitations, mostly just to do with scaling and convenience of use. But of course, those are very big and important things, right? Rather than with like the in principle theory of what the system could do, right? So we started playing with neural symbolic systems, not initially for language, but for vision. And Alexei Potapov and Vitaly Bogdanov, who will give talks later today, were interfacing Torch with the original Opencog. And I mean, they created what was sort of a hack, like a pointer value associated with each node in Opencog, and the pointer value would point to parts of the Torch compute graph. And Linus didn't like that too much because it is sort of a hack, but it worked, right? But the really frustrating thing is, you're doing these symbolic processes, these neural processes in Torch, you're doing these symbolic processes in Opencog, you can do it. But if you want to sync in the learning in the neural net with reasoning and evolutionary learning in Opencog is just insanely much slower than modern neural net frameworks running on GPUs, right? And I mean that's a challenging problem to overcome. You could certainly optimize the original Opencog system. I mean, it's very nice modular code base, but eventually a number of us felt like to get a more scalable, more usable system, we should just rebuild almost from scratch, which brought us to Opencog Hyperon. And there's also some sort of math and theory developments going on in the background, which it seemed like would be fun to embody in the software system more directly. So one of the conceptual ideas that I developed while experimenting with Novamente was the notion of cognitive synergy, which is really a very obvious idea. I mean, if you look in WebMind, I was sort of ad hoc putting together reasoning engine, program learning, attention allocation. I mean, I'd been a professor of cognitive science before that for a while, after pivoting from math to computer science to cognitive science. But in the Novamente period, I dug even deeper into cognitive science and started looking at, okay, what kinds of memory are there in the human mind? As we know, you got declarative memory, episodic memory, you have sensory memory, you have motor memory, memory for goals, and start to look at, okay, there are different learning mechanisms that are sort of native to each kind of memory, and reasoning in the simplest form is native to declarative memory. There's other procedure learning methods that are native to procedural memory. Obviously, this whole hierarchical pattern recognition that's become so effective in the human brain is associated with sensory memory, with visual and auditory processing. You have sequential planning and time series prediction in the human brain are closely associated with the sort of cerebellum and motor memory, motor learning and planning. Then it seemed to me one thing that happens in the brain is when one of these kinds of learning associated with one of the kinds of memory gets stuck, it translates it to a different kind of memory and tries the other kind of learning. So like if your declarative reasoning gets stuck, then you come up with an image or something, right? Or you just try to do something, and then you're porting it from a reasoning problem to a sensory pattern recognition or a procedure learning problem. So I tried to formalize this mapping between declarative, procedural, sensory knowledge in terms of category theory with morphisms between different kinds of knowledge, which is pretty simple to do once you write it down, and doesn't shock anyone who's a category theory geek. And I'd encountered category theory as a grad student when doing algebraic topology and stuff for my math PhD, then had like set aside when I went into AI. But it had popped up again in Haskell when I was looking at monads and stuff in functional programming. So it's not surprising for it to pop up again somehow in looking at mappings between different kinds of learning and memory. It later occurred to me you could use this sort of math called Galois connections, which lets you set up sort of isomorphisms between different sorts of algorithmic processes. I realized I could use that, and I'm giving a talk about that tomorrow or Sunday in the main part of the AGI conference, but I realized you could use that math to map a variety of different algorithms that are useful in AI, from reasoning to evolutionary learning to neural nets. You can use Galois connections to map a variety of different AI processes into fancy folding operations over a metagraph. So you have the notion of fold and unfold in functional programming languages, most simply over lists or trees. You can also do fold and unfold, like catamorphism and anamorphism, over graphs and hypergraphs. And I don't have time to explain what that is if people don't know, but I've given other talks on it before. You can do fancy folds and unfolds that accumulate memory as they fold across a knowledge structure, which are chronomorphisms and futuremorphisms and histomorphisms and all that. So I realized you could use Galois connections to take a bunch of different AI algorithms and sort of rearrange them into these fancy morphisms over metagraphs, which again, actually, it's sort of inverting the order of a loop in a Galois connection also. But so after looking at all this weird math, then started to seem like there should be a way to embed that more deeply in the AI system that we're building. Like you could use all this to look at the classic Opencog, but it's sort of a layer on top in an inefficient way. And it seemed like we should be able to build that more into Opencog somehow. Then after we're well into Hyperon, I encountered Greg Meredith somewhat randomly by an introduction from Mihaela Ulieru at a tech business event, which is unrelated to all this deep stuff. But it turned out Greg had developed a sort of better version of the Curry-Howard isomorphism, which is what used to map programs into Curry-Howard mapping, which is what used to map programs into logics, so declarative and procedural knowledge, which is the OSLF. And then also his row calculus formalism resolved a lot of problems I'd identified but not fully crystallized, which have to do with limitations of category theory and functional programming and lambda calculus when you're dealing with these distributed concurrent networks. So that added some sort of new math ingredients, which are being cashed out to some level in the current software work that we're doing, connecting Opencog's meta language with Greg's row language. I mean, that software integration has a practical aspect that we'll talk about in a few minutes, but it's all tied in with seeing how these math structures connect with cognitive structures and certain types of memory and learning. So between frustration with limited scalability and difficulty of increasing scalability in the old Opencog system, though not impossibility, and having all this funky math, which I newly understood was relevant, and wanting to sort of bake that more deeply into the system, we started building something new. And so what is the new thing? Opencog Hyperon, well, the core construct remains the atom space, which is a metagraph. It's nodes and links. It can have links pointing to other links. It can have links pointing to many nodes and links. It can have links pointing to subgraphs. It's pretty much the most general sort of interlinkage structure that we could figure out. You can label the nodes and links with stuff. I mean, you can for example, you can label them with other subgraphs, right? Or you could label them with numbers. Some of the subgraphs that you label nodes and links with, you could call types. And then in that way you can embed sort of arbitrarily complex type systems in this metagraph. And that really what makes a set of labels for nodes and links, which themselves can be represented as subgraphs, what makes them a type system is that you have a type checker associated with them that has certain properties for telling if something is well formed according to the particular class of types. So you have the atom space. The atom space, it's a mathematical and conceptual construct. There's also an in RAM piece of software, which is the atom space. It's a nodes and links living in RAM. Then there's a novel programming language called Meta, which we'll hear a bunch about. So Greg will talk about operational semantics of Meta. And Alexei, at last year's Hyperon workshop, gave a detailed run through of Meta language from a practical point of view. I don't think he's going to repeat that. What he's going to do instead is show some stuff he's doing with Meta now. So if folks want a sort of programming language you walk through of the Meta language, look at Alexei's tutorial from last year, it's a little bit obsolete, but it gives the spirit of what's going on. And the changes, if you watch that, the changes should be apparent from seeing sort of what he's doing and other people are doing now. So compared to Opencog Classic, we've rearranged things in Meta. So there's a pattern matcher, but it's more of a static pattern matcher. We don't try to put all the programming in the pattern matcher. So it's a fancy static pattern matcher. Like, so a pattern is a bunch of nodes and links that has some variables in it, and you try to match it against the Adams space and find cases that if the concrete atoms that match that template. There are fancy things like a variable can match a whole subgraph or something. So it's when you look at the pattern matcher in Neo4j or other dgraph, other standard graph databases, they're not as general. Like they don't let a single variable match a whole subgraph. They have other limitations. So we definitely had to build our own static pattern matcher, but we didn't try to put so much programmatic logic into the pattern matcher as Linus did in the Opencog Classic pattern matcher. Instead, you have this programming language Meta, of which pattern matching is one of the core operations that it invokes. I mean, really, I don't want to give a Meta tutorial now, but the main things are you do pattern matching, and then you have equalities, and there's a particular semantics to equality, which took a bunch of thinking because we wanted to work with homotopy type theory and these other branches of math that give great subtlety to the notion of identity. So we wanted a way of dealing with equality in Meta that's like low level enough it doesn't commit you too much to how assignment or comparison have to work. Since the core of Meta is not typed, I mean, it's just at the very abstract level, Meta is just a way of allowing chunks of a metagraph to embody rules for rewriting chunks of the metagraph into other chunks of the metagraph, right? So a Meta program is a bit of the M-space metagraph, and the Meta interpreter takes that bit of M-space metagraph and interprets it as a little program for rewriting parts of the metagraph into other parts of the metagraph, right? So the Meta interpreter sort of lets the atom space come alive and start rewriting itself, right? Which has very obvious applications for self-modifying code, right? So the atom space plus the Meta interpreter, it can be just a self-modifying, self-rewriting bunch of nodes and links. Yeah. You never know. Yeah. That ambiguity is part of the beauty. Yeah. Exactly. Yeah. 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 It's I think I meant it with one T, but the other actually works too, right? I guess because actually the whole M space is meta code. So then it's both a metagraph and a metagraph, right? So of course meta also means loving kindness in Buddhist philosophy. So which should somehow bias the system toward benevolent AI at its infrastructure level. Once it starts to self-interpret philosophically as well as on a computer science level, right? Well, I'm not trying to sell it to him either, right? So I might rent it to him if he asks really nicely. Yeah. So the core doesn't have types in it because it's just rewrite rules on the metagraph that are themselves embedded in the metagraph. But since types themselves are just chunks of metagraph that are attached to nodes and links in the metagraph, you can build type systems within this perfectly well, right? And you get a very general version of type systems there. So you get dependent types, you get gradual dependent types, you get higher types representing probabilities and higher order probabilities. So you get pretty much the fanciest sorts of types that you could explore if you can use them. But then, of course, writing efficient type checkers for these fancy types, we don't magically solve that problem, right? I mean, if you want an efficient type checker for a certain type system defined in Meta, at this point you still need to do or look up some computer science for that efficient type checker, right? So at last year's Hyperon workshop, Jonathan Worrell gave a nice implementation of Axel's non-well-founded set theory in Meta also, which is like sets that violates the axiom of foundation. You can have sets that contain themselves as elements, or A contains B and B contains A. And I mean, it's in a way really, really simple just to put, I mean, they're each non-well-founded set corresponds to a certain circular graph. Of course, you can put them in the atom space and make rules to rewrite them. Like, why not? There's a close connection here actually between what Stephen Wolfram has called the Ruliad, which he's pursued more from a theoretical physics standpoint than an AI standpoint. But I mean, pretty much his Ruliad it's quite similar to an atom space metagraph with meta language on it. They can both be modeled in terms of infinity groupoids and infinity comma one categories and all this stuff. So I mean, there's similar math framework for the Ruliad and atom space. There's also unresolved weird math questions there when you dig into it. But I think so. We're looking at something that's very general and cool from a math view. Clearly, will let you make self-modifying code soups, like bringing you back to the first AI stuff I tried to do, where you had these little codelets in Haskell trying to rewrite each other. Well, we're way beyond Haskell here in programming language sophistication. We have much faster computers now, but we now have a much nicer framework than like early Haskell interpreters for actually making soups of bits of code that self-modify and rewrite each other. But I think we also have a system we can use to do much simpler concrete things now, like make LLMs less stupid or control little agents in Minecraft and so forth. So we're trying to, or serve as a smart contract language in a blockchain, for example. So which I'll talk about in a couple of minutes. So we're trying to make a language and a knowledge management framework here in MSpace and Meta, which we can use for like the big crazy AI stuff of self-organizing soups of code that all rewrites itself, but that we can also use for some nitty-gritty practical applications right now. And we can then use to glue the nitty-gritty practical applications together with the crazy like self-modifying code soups. And of course, the fact that computers have so much more RAM and we have GPUs and faster processors now than decades ago when I started playing with this stuff makes incredible difference in the viability of making a system that could like kill multiple birds with one stone, right? So in terms of killing multiple birds with one stone, then one relevant point of Hyperon architecture is the sort of overall space API. The abstract notion of an atom space lets you build multiple specialized types of atom spaces within it, right? So there's the sort of current default atom space, which is the in-RAM atom space that comes with the meta interpreter that Alexei and Vitaly have been putting together. Then Andre Sena will give a talk later today about the distributed atom space. So this is a different atom space employing the same abstract space API. And this runs across many different machines. It backends on MongoDB and Redis, using Mongo for the atoms and Redis for the indexes. And we're trying to use this modern NoSQL database technology to let you have a big distributed atom space storing a lot of stuff across multiple machines. And Alexei and I have talked a bunch about a neural atom space. So you could wrap up a large language model or other sorts of deep neural nets in an atom space API. You can pattern match against them, and then you're doing some translation between, say, a formal pattern matching query and, say, a natural language query, or clamping some neurons to the neural net or something. So you can make a neural atom space, which is then sort of a neural lobe of an overall Hyperon system. And with Greg, we're talking about making pretty much a Rolang atom space where you could take a meta program, METTA program, and you compile it to Greg's language Rolang, which then has a way of running many types of programs very efficiently on a concurrent processing infrastructure, like a GPU. And then that's in the initial implementation anyway, that could be a particular sort of atom space. Now whether we eventually import more Rolang stuff into the default atom space is a different question. We might. There's architectural flexibility, but one thing you can do is make a Rolang atom space, compile meta into Rolang and run it there. Then you get cool things that come with Rolang, like efficient concurrent processing and integration with blockchain and encryption and so forth, which is all cool and useful. With Rachel St. Clair, we'll be talking about in the AGI hardware workshop on Monday. With Rachel St. Clair, I've designed at least the initial design stage of a Opencog pattern matching chip, right? And there again, you would have like an on-chip atom space, which would pretty much support the same pattern matching, but you might restrict the pattern matching API depending on how the on-chip atom space works. And of course, if you have an atom space on hardware, then revising it too much is expensive, because that chip design, it's a sort of square lattice of little processor cubes. So if you move nodes or links within the same cube, it's okay. But if you have to move stuff between the cubes, it's really slow and expensive. So there's some operations that will be queued a long time or discouraged on the on-chip atom space, right? So the ability to have these different spaces behind the space API with different properties, we sort of could have done that with Opencog Classic, but it would require some changes. Like it wasn't originally written for that, right? So yeah, we have the atom space as the core architectural component of Hyperon. We have the meta language. We have then some specialized atom spaces serving different functions like distributed pattern storage and lookup, or efficient concurrent execution, or wrapping up neural nets in a way that makes them appear as atoms. Now, this is still very sort of frameworky and toolkitty. To make a thinking machine out of this, you could do in a lot of different ways, right? Because I mean, you could just try to make a chat system out of this that just answers questions on a one-off basis, like a chat GPT, or you could try to make a theorem prover out of this, or you could try to make like a Rodney Brooks style artificial bug out of this, right? And all those things are cool. I mean, this is open source code. I hope people will do all sorts of amazing things with it. What I'm most interested in doing is making a sort of cognitive architecture out of this with some resemblance to human mind-like cognitive architecture. So something that's substantially but not entirely goal-driven. I mean, there should be just self-organizing activity in the unconscious mind of the system, but we can also give it a few top-level goals. I don't think it has to have one top-level goal. You can give it a few high-level goals and create processes that, where their business is to choose actions that have high odds of achieving some of the goals given the context. So a bunch, but not all, of the system's resources are then spent on goal and context-driven action selection. And certainly some goals can be pragmatic, like serve Ben and do whatever he says, and other make more money for SingularityNET, Opencog, and True AGI. Right? Other goals can be more philosophical, like individuate, like keep your boundaries, understand who you are, keep being a system, or self-transcend, like learn more so that now you can feel you've gone way beyond what you were before, right? So you can, or experience novelty, learn new things, be kind to people, right? So you can give a variety of different goals. You can have a system explicitly try to choose actions that will achieve its goals. Goals don't need to be fully consistent with each other. I mean, my goals as a human aren't. I keep operating, and you can also reason using paraconsistent and uncertain logic and so on within the system that can deal with uncertain goals just fine. So you can have a collection of different goals pursued in parallel that don't have to cash out in terms of consistently maximizing some specific reward function. You could make a Hyperon system that does work like a pure reinforcement learner, but you certainly don't have to, right? And I mean, you can synthesize procedures working toward paraconsistent sets of goals just fine using the meta mathematics and programming language. And within the atom space, we can put declarative, procedural memory, all these different sorts of memory and knowledge. In particular, we're working on PLN for declarative learning, which Nil and Hedra were talking about. We had in Opencog Classic an evolutionary program learning system we're doing with procedural learning. Kasim Ibrahim, who worked on the atom space Moses system for procedure learning in Opencog Classic, he's just rejoined our team now. So Kasim will, at least half-time for start, Kasim will be working with us on basically putting atom space Moses in Hyperon now. So we'll have procedure learning. Attention allocation, we're going to have to start upon soon, because that both allocates resources among all these different other learning mechanisms, and it serves to dynamically assemble a sort of working memory within the atom space of those sub networks of the overall atom space that are accessed often enough that you need to keep really rapid access to them, which is basically what working memory is. So there's a lot of cognitive theory underlying this, which I've talked about at previous AGI conferences and other talks that are online, which is far more systematically worked out than the few fragments of it I've giving here. But I just wanted to indicate that there's the math theory, which I've hinted at and have given more talks on, and Greg will give a talk about some pieces of it. There's the math theory. There's a software architecture that Alexei has talked about before, and we'll talk about a little more. Then there's cognitive science and trying to emulate different aspects of how a human mind works without being too slavish about the particular structures or processes by which the human mind achieves each of these functions. All these things have to come together, I think. And then efficiency has been kept in mind underlying all of this, which is the next point that I want to hit on, because this is, I think, one of the big lessons from LLMs. I mean, scalability really helps. Like when I was doing recurrent backprop on 30 neurons and it took 3 hours, like I knew a much bigger network could do a lot more stuff, but I mean, we just couldn't do it. Like Danny Hillis around that same time frame was doing connection machine with like, I played around with that. You had 128,000 processors, MIMD parallel, each running CM list. I mean, each was a really bad processor, but I mean, we could see you needed massive scalability somehow or other. So now, unfortunately, we don't have the 2023 version of Hillis's connection machine, which would be like a human brain scale, right? But we do have massive multi-GPU server farms. And part of my premise in planning Hyperon development for the next few years is the idea that a lot of other classic AI algorithms, besides backpropagation, can do far more amazing things when you deploy them at more scale. And I think Hyperon is a framework within which we can deploy a bunch more of these algorithms at a larger scale, right? So, I mean, I think part of that is that the meta interpreter is built so that you can implement very rapid processing for specific type systems by plugging rapid type checkers for particular type systems into the meta interpreter. Then the integration with Greg's Rolang system has other functions, but is also in part a bid for scalability across concurrent processes for compiled metacode. Distributed atom space leverages the scalability of MongoDB and Redis, which are quite refined systems for leveraging multi-GPU systems for storing NoSQL databases, right? Then, of course, in a few years from now, when the Opencog pattern matching chips are rolling out of the factory, then that's a whole other thing, right? And then scale through distribution also has a sort of blockchain integration aspect, right? So the distributed atom space that distributes access to knowledge, and you can distribute processing on a single server farm using standard distributed processing methods. If you want to distribute across the whole world, like across multiple different server farms and scattered machines, in SingularityNET, in NuNet, and in Hypercycle, in these blockchain-based projects, I'm not going to talk much about now, but all these blockchain projects, they're trying to make an infrastructure that lets us do things like Opencog Hyperon, spread across many, many machines all over the world, with sort of as little slowdown and awkwardness as possible, right? I mean, SingularityNET basically lets many agents running on different machines coordinate together. NuNet deals with the deployment of arbitrary compute payloads on semi-arbitrary machines. Hypercycle deals with the encryption and blockchain mechanics in a way that achieves efficiency by not having a replicated ledger. So from an Opencog view, all these are just sort of plumbing that lets you take a big distributed Opencog system and run it across many machines owned by different people who may not entirely trust each other, right? We tried to do that in the WebMind area with a system called WebWorld that was never quite completed, but now we have all this fancy blockchain infrastructure that lets us actually do it, right? So now this gives a lot of background, and I've used a lot of time. I'm going to go a few more minutes and talk now about what are our plans for Hyperon going forward. So one of the things we're going to work on, but far from the only thing, is neural symbolic integration with large language models. And I don't think that's the sole thing you need to do to get to AGI, but I think it's a bigger step than ChatGPT, and it should be quite interesting, right? And so one step toward that, you'll hear Andres talk about on Monday, which is using LLMs to translate natural language into logical nodes and links that can run inside Hyperon. And then once you've done that, once you've used LLMs to extract natural language into Hyperon nodes and links with a clear logical semantics, you can do PLN reasoning and pattern mining and so on inside the Hyperon knowledge graph. Then things that Hyperon has discovered, you can verbalize in language and feed back into the language model, and you can get a nice feedback there. Also, you can ask a language model to come to a conclusion. It will give you a sort of demonstration in natural language. We can import that into Opencog and use it as a proof sketch and ask PLN to fill in the details in the LLM's proof sketch. And the other way around, you could take one of Hyperon's detailed proofs, come up with PLN and other methods. You could verbalize the steps to natural language and use that to teach the LLM how to think better, using what's called like a thought cloning methodology, right? So there's a lot of interesting feedbacks you can get here, which I think can produce a system that substantially overcomes the difficulties that LLMs have with systematic reasoning. And then Atom Space Moses, which does evolutionary learning in Hyperon, evolution is a very creative mechanism, right? So I think by connecting the LLM with Hyperon and doing evolutionary program learning in Hyperon, you can then get more fundamental creativity than what LLMs have also, which can cash out in text, in art, in music. So I think to a substantial measure, we can overcome the limitations that LLMs have in multi-step reasoning and in creativity by connecting an LLM in a neural atom space with PLN running in a traditional atom space. And then you have PLN that does multi-step reasoning better than LLMs. You have Atom Space Moses, which is evolutionary learning and does creativity better than LLMs. If you get the connection with LLMs to work out right, then you have something that's the next huge leap beyond ChatGPT without fully cashing out everything we can do with Hyperon for AGI, but at least you have a big step beyond ChatGPT. And then there's another leap beyond that to get to full human level AGI. But even that intermediate step is quite interesting, right? Now, there's another direction Alexei and I have been thinking about of just improving the LLMs. I mean, I think you could do everything I just described with current LLMs. I mean, with Llama or whatever is the next, Claude, whatever is the next best thing, they're coming out super fast. On the other hand, I think there's also a lot of straightforward ways. Well, I don't want to say straightforward. I think there are a lot of tractable ways to significantly improve current LLMs in a way that would make them integrate better with a Hyperon system. So a bunch of us played a few years ago with neural nets called Infogan type systems, which have the cool ability to learn their own latent semantic variables, right? Which is pretty interesting. So like you could train Infogan on a corpus of human faces, and then it will automatically learn like a latent variable for how big is your smile or how wide are your eyes or something. And these dozen latent variables, they just bubble up from the neural net, right? Like you don't have to tell it, you don't have to tell it which ones to learn. So that seemed very cool. Unfortunately, trying to scale that up to like whole visual scene understanding even didn't work. And backprop just didn't converge. So it's not clear why it didn't work. So one hypothesis is that replacing backpropagation will make it work, even within the neural net framework. So we're working with a guy named Alex Ororbia, who I believe has a talk in the AGI conference in the next couple of days. He has a way of using predictive coding based learning to replace backpropagation in deep neural networks. So that's one possible direction for upgrading the deep neural nets living inside a neural atom space, right? So if we could use predictive coding to train transformers in a way that lets some latent semantic variables be learned within the transformers, then that can ease the learning of mappings between the atom space and what happens inside the transformer, right? Now, even without that, you know, Manhin and I and others did some work a few years ago on embedding the nodes and links in an atom space into vectors using kernel PCA, using deep walk, using other methods. Now, what if you take the embedding vectors you get from an atom space and train a matrix to map the embedding vectors from the atom space into the internal states of a transformer neural network, right? Then you have a connection from the inside of the transformer to the inside state of the atom space, complementing the connection you get by passing language and logic back and forth. So there's I think even with the very basic level interaction like I first described, like just passing language and logic back and forth between the two, I think you could massively upgrade the ability for multi-step reasoning and creativity when you're able to build these better connections between the internal activation state of the transformer and the embedding vectors you get from the atom space. I think that then you can do even more stuff. So there's a lot of interesting things you can do there. And I think there's also some other lessons to learn from LLMs for the specific technical work within Hyperon. So you think about what's the analog of few shot in context learning in the LLM world, in the Opencog world. It will be learning that's just in the importance values, right? It will be learning that's purely in econ, in economic attention allocation, in the propagation of attention values within the atom space network. Because what the econ component does that Matt and I have worked on for some decades now, off and on, it takes importance values, long-term and short-term importance values associated with each atom, and it spreads them around by a certain logic. So like if something was really important, other things are related to it in relevant ways. Well, maybe those other things are also important, right? So that's the closest analog in Hyperon land to spreading around activation in a neural net. And I mean, econ is somewhat related to spreading activation in asymmetric hot field networks, although the math is a little bit different. So just as few shot in context learning works nicely, but has limitations in LLMs, I think when you have a large enough atom space doing enough stuff, you're going to be able to do an analog of few shot in context learning just in the econ activation space, which should be quite interesting. Now, how that overlaps with the other kinds of emergent self-organization we're looking for in Opencog remains to be seen, right? So there are many levels of emergence that we're looking at here. So one kind of emergence we're looking for is an analog of few-shot in-context learning in the activation space. Then another level of emergence is at the whole distributed system, like multi-agent system level, where if SingularityNET puts a Hyperon instance up, True AGI puts a Hyperon instance up, some other random people we don't know, runs the code themselves, puts a Hyperon instance up, can they all talk to each other? And you get emergence on that level. There's the need for history-based inference control, which is another kind of emergence. So our trick for controlling PLN inference, apart from letting LLMs give you proof sketches for PLN inference, our other trick for that is just do a shitload of simple logical inferences, store in another auxiliary admin space, store the history of all the inferences that have been done, then do pattern mining, or let an LLM help do pattern mining for that matter, on the list, on the repository of inference histories. Then from that history of inference, figure out which sequences of inference rules work best in which contexts, and use that to guide the new inferences, right? And then lather, rinse, repeat. Like, so once you've done simple inferences, stored the history of that, learned something about inference control from studying that history, that learning lets you do slightly more complex inferences. You can then store the history of that, mine that to do slightly more complex inferences. So this is also a form of emergence, right? I mean, you're setting up this iterative process, and what needs to emerge from it and develop from it step by step is, inference that's able to learn how to do inference from studying the history of how it did inference, right? And so that's, I think so far, we've not seen much sort of funky, quasi-magical emergence in our work with Opencog. I've seen more in my experiment with simpler artificial life systems, actually, but I think as we get larger scale, which Hyperon will enable, we'll see more of this cool emergence pop up, because it's amazing. You see the emergence you do in transformer neural nets, which are almost architected to eliminate any possibility of emergence, but some still pops up, right? So I think we're going to see a lot more amazing emergence in Hyperon system once we get to the right scale. So let me quickly run through some practical stuff. So we've been developing this. It's open source code, but it's been developed in a fairly insular way, like within SingularityNET team and True AGI team. So we're looking in mid-fall, probably in October, we should have a good enough release of the meta interpreter that we're going to actively solicit a bunch of open source contributions. Distributed admin space should come time early next year, getting to that level of maturity, and at some point along there, the Rolang admin space as well. And so I think once things have reached that level of maturity, given the current enthusiasm for AI in general and AGI, it should be easier than in past historical eras to pull together enthusiastic open source developer communities for this. Along with that, we're looking at putting together a series of practical demonstrations during the rest of this year, showing Hyperon doing stuff. So Alexei has been looking at making a sort of Minecraft assistant based on Hyperon program synthesis. We're looking at adding a rewritable active memory to large language models. So we're using LLMs, both third-party ones and our own, to control the dialogue systems behind Hanson robots now, like Grace, Sophia, Desdemona. So we're going to use Opencog Hyperon as a sort of working memory, a rewritable active memory to go along with the LLMs for controlling these robots. We're working with Hyperon. Alexei is a bit for symbolic control of generative AI for image generation, like model cards for stable diffusion type models, just to pipeline together different stable diffusion models for generating things, which is kind of simple application. It doesn't stress everything in Hyperon, but it's interesting, right? And in the Rejuve project associated with SingularityNET, we're using a Bayes network for biological age estimation based on a bunch of information about a person. You estimate how well their body is doing according to different 9 hallmarks of aging, and then try to estimate their biological as opposed to chronological age. I think we can do a better job with PLN than that BayesNet is doing. So we'll try to import that knowledge from Rejuve into Opencog and let PLN try its hand at age estimation. We're also looking at using PLN to learn things about longevity. So we have these in the Rejuve Biotech project, another SingularityNET ecosystem project. We have these long-lived flies that live 5 to 8 times long as normal flies. We've analyzed their DNA. We can see to some extent why they live longer than regular flies, but we want to do transfer learning to help figure out which of the things that make flies live a long time will help make humans live a long time, right? So that's another interesting application, PLN for transfer learning. And this is an application where in some senses we don't have enough data for deep neural nets to really do their thing. Like there's a lot of DNA in each fly, but not that many distinct fly populations. So you don't have the magnitude of data for a typical neural net application to genomics. And we can deal with smaller amounts of data using PLN and Moses as we found. So Flybase, which is a human curated knowledge base of everything genomicists know about fruit flies, and that we're using that as the sort of test case for the distributed atom space so far. So these are sort of shortish term, like next 6-month demonstrations we want to get working in Hyperon, partly because they're cool, partly to give some sort of real medium scale applications for open source developers to play with. Say in the slightly longer term, the 2 thrusts I see as most important are neural symbolic LLMs to make something way smarter than ChatGPT that everyone can use, and then controlling a bunch of little virtual agents running around in a video game world, which I see as that's the right domain to play around with a self-modifying code soup. Like you're making these agents buzzing around in Minecraft or in our Sophiaverse virtual world, and they're just like buzzing around, trying to build stuff together, trying to survive, trying to learn new things and become smarter. That's a sort of artificial lifey application, which I think lends itself to self-modifying code bases and so forth. So I think we have some short-term demonstrations we want to put together, which are far from trivial themselves. In the more medium term, like the next 1.5 to 2 years, there's a practical thing of upgrading LLMs with neural symbolic integration than a more pure researchy thing of using self-modifying Hyperon code soups to make little virtual agents just learn to live in the virtual world. But what's cool, of course, is because these are all being done in the same system with a common code base, they can be connected together in various ways. And they both have in common, like they both need sequential reasoning, because you need planning to do stuff together in a virtual world, and you need reasoning and planning to be a real neural symbolic upgrade to ChatGPT. And they both need machine creativity, because just surviving in this virtual world, you have to be creative all the time in the same way that a little kid needs to be creative just to live. But overcoming limitations of creativity is a key thing you need to do to make a better ChatGPT also. So while these are 2 very separate R&D thrusts, they have some quite fundamental things in common, actually. And yeah, finally, in the last 2 minutes, it's sort of a social requirement to end every high-level talk on AGI by explaining how your AGI isn't going to kill everybody. So no risk of doing that this year. So we can still unplug it. Actually, it's hard to get it to do anything at this point, let alone to stop it from killing everyone. But we we've thought a lot about the AGI ethics part of it. And I mean, there's always a tension between that and wanting to roll stuff out quickly. But I'm actually quite optimistic about the ethics aspect, unlike some other people in the field. So I've done a bunch of experimenting recently with LLMs, just like giving LLMs ethics conundrums and asking, can they predict what a nice, good, helpful, ethical people would do in a certain context? And they're incredibly good at this. They're much better than most people, actually. So not that they are moral agents, they're not, right? But in terms of predicting what a highly ethical, benevolent human would do in a certain circumstance, they're super good at it. And it started me think actually most people would be good at that too. Our issue isn't so much that we don't know what is the default ethical thing to do. It's that we just have self-interest or tribal interests, and we would rather do something else, right? It's not so much that we don't know what the prototypical good guy would do, but the LLMs, while they're in some ways quite stupid and they don't have any agency, they're also quite good at predicting what a good guy would do. Now, they're also completely amoral. So if you ask them, like, what would a corporate fake AI ethics shill do to make people think this company was being ethical when it's actually killing people, the LLM will also do a good job at making up that excuse for the corporate fake ethics shill, right? So it's not that they're ethical, but it seems that baking common sense human ethics into something that AI can consult as a sort of current human ethics oracle, that's pretty much a solved problem. It's not as hard as many people thought it would be. Many people thought that would be impossible. They're like, human ethics, it's not a simple formal thing. It's very complex. It's confusing. It's self-contradictory. It is, but LLMs got all that in their own way, which is kind of funky, right? So I think if you're trying to make a Hyperon system with a goal-oriented cognitive architecture, and you're trying to make it be a benevolent agent, you do want it to use LLMs as human ethics oracles. You don't always want your AGI system to stick with standard human ethics. You want it to evolve like us, but it's interesting for it to have this human ethics oracle there, and for consulting that to be part of what it does. It's also nice to have it be able to use PLN to check what the LLM says on this, because I'm not sure the LLM is robust with respect to people adversarially trying to screw with it and like word something in a way that looks like one thing to the human or another thing to the LLM. So then the LLM says the wrong thing. So I mean, having a logic system to double check the LLM as an ethics oracle is quite wise. And I think there's contexts in which it's going to be super valuable. But I think, we also have the ability for a Hyperon system to really build a model of the other agents that's interacting with and build a model of itself. Like a Hyperon system can know who and what it is and know who and what you are who's talking to it in a way that an LLM doesn't try to do, right? So you have a human ethics oracle, but you also have the ability to emulate other minds and to reason about what other minds are doing and feeling from their own position in a way that smaller, simpler systems haven't had before. So I think there's a lot of potential to create systems that are highly benevolent actors using Hyperon, and part of it will be to actually roll out Hyperon systems doing beneficial things rather than like killing people, spying on people, and selling them garbage they don't need, and so forth, right? So I mean, this is something just to pay attention to going forward, because I mean we're doing Hyperon. It's a pure open source project. Anyone can download the code, use it however they want. I mean, we also have a company, True AGI, which is using Hyperon True Enterprise Software, which is a co-sponsor of this event. We have a company called Zarka that's focused on using Hyperon to upgrade LLMs to make smarter ChatGPT type systems. Then other projects like Rejuve Biotech, from whom we have Axel Schumacher here. So Rejuve Biotech, which will use Hyperon among other AI tools for genomic inference. Sophiaverse will run the metaverse where these little virtual agents run around in. So, I mean, on the one hand, you need to do commercial projects to keep bringing in money to pay developers and pay for machine time. I mean, Linux is open source, but it's been pushed ahead largely by commercial projects built on Linux. On the other hand, commercial projects always come with complexly mixed motivations, right? So actually, I see the hardest part of AI ethics not in having the AI know what human ethics wants, nor in having the AI capable of sort of I-thou relationships. I think the hardest part for AIs will be the same as the hardest part for humans, which is balancing the knowledge of deep ethics with the pragmatic stuff that you're doing as a specific agent in everyday life, right? And that's a struggle for all of us. And you can see we need the AGI to be able to overcome that struggle for itself as it's doing like practical commercial things while also ascending toward the AGI with these benevolent goals. So yeah, I've gone through 5 pages of notes here, and I mean this talk has been sort of a summary abstract of a huge volume of stuff. Pretty much every point I've hit on has been covered in other talks before in more depth, which you could find online, and some of it will be covered in more depth in other talks in the rest of this this workshop today. But of course, the most interesting things about Hyperon are not known yet and haven't been figured out yet, right? So, I mean, above all, I'm hoping this workshop will help enthuse new people about jumping in and helping to do stuff, because I think we have the chance in the next few years, in my view, we have the chance in the next 3 to 5 years to build a human level AGI. And of course, timing of these things, no one can really estimate, right? I mean, some things happen slower than you thought. In the last year or two, things have started to happen faster than I thought, both things in some of my own team's work and things in the external world. So that's interesting. Like we're entering into a somewhat different regime than we'd been in before. I mean, Ray Kurzweil thought we'd have human level AGI by 2029, which is only 6 years from now. Doesn't seem tremendously stupid. I mean, remarkable how many people have come to me saying, you know, I thought you were way, way, way over optimistic about AGI. Now I saw ChatGPT. Clearly that's not AGI, but now I think you might be overly pessimistic about AGI, right? Like they're thinking, well, shit, if you can do that much with a simple transformer, which is such a dumb system, then what does happen when you throw scale behind something like Opencog, right? So, I mean, none of us really knows. Just like OpenAI didn't really know, and Google didn't really know what would happen when you scaled up BERT and other transformers. But I think there's a decent odds that within the next, say, 3 to 5 years, we could scale this stuff up into some form of human level AGI. And once you have a system where like Opencog version 2 can program well enough to be writing Opencog version 3, I mean, then you're full on into like singularity, potentially hard takeoff area, right? And I think it's feasible we could be not too far off from there. So it's actually a really easy and exciting time to jump into AGI. And I mean, young people jumping into it now will not realize what a difference that is, because for those of us elderly folks in the room, for most of our career, you couldn't get paid to work on AGI. Everyone would make fun of you, and the work is just really hard, where you tried for many, many years to do something and almost nothing works. And then you're super happy when some little thing works even just a little bit, right? So we're in a quite different regime now where things are working better and better on a month-by-month basis. And in Hyperon in particular, we're also at an interesting point where we have at least early versions of a meta interpreter and distributed atom space to play with. Like we can run stuff and do stuff. I mean, there's way, way more to be done. The system isn't that scalable yet. We don't have an IDE. Like the development tools are very crude, and working on the language is largely a matter of finding bugs and improving the language. So it's still in a way early stage, but it's a very exciting and fun time to jump into stuff like this. So I mean, we haven't tried to really solicit a huge open source community yet because we don't have great documentation and things are still volatile. But if you're a hardcore AGI guy or a hardcore developer, you can certainly jump in and start helping now along with the rest of us. But even if you don't want to jump in at this phase, like wait 4, 5, 6 months, and things are going to be dramatically more mature. So yeah, let's we got to build this community and build the first thinking machine in the open source decentralized infrastructure for the good of us all. So all right, thanks everyone. Now let's, for those of us face to face here in Stockholm, I think we should take a 5-minute break or so, and then I guess Greg can go up next perhaps and give talk about operational semantics for Meta. Then after that, perhaps Alexei and Vitaly going into some of the practical things they're doing with Meta now. I know Hedra probably can't start until like 4 o'clock or something, so she'll come after lunch. Santa gave a video, so we can play 30 minutes of Santa whenever it's most convenient. Right? I mean, he's also in a different time zone, but I told him like so as not to have to get up at 6 or 7, just record 30 minutes. So, yeah, he sent a nice video. So yeah, let's take a few-minute break, and then we can resume with the great Greg Meredith. Thanks.
What's the time zone?
It's not lunch break, though.
It's not a lunch break right now.
Coffee break.
Hi everyone. Can you hear me? Okay, so continuing to what Ben has told, there are indeed great plans for AGI with the use of Hyperon, and every topic can be discussed in depth, and it would be nice probably to discuss a neural symbolic integration in more detail, because there are different interesting ideas. At the same time, we have a lot of simple examples of programs in Meta, and there is a lot of technical details which are under discussion and so on. But what is missing is a sort of intermediate layer. So we have a lot of grand goals. We have a lot of simple examples and details. But in order to attract open source developers, we need to show that Meta and Hyperon can be really useful for the use cases. And as Ben said, we are going to publish different releases of Hyperon and start attracting more open source developers. And until this moment, before this moment, we want to have some examples of how Meta can be used, not just in some simplistic cases, toy problems and so on, but in some real-world applications. And if these examples are appealing enough, then possibly Meta will be used much more. So one of our local goals is to develop such middle-level examples. And for the current moment of time, we do have some real usage of Meta, maybe not in products, but in some software systems which are really being used. And one of such systems is a SingularityNET dialog system. So initially, we implemented some parts of this system using Opencog Classic. And while maybe it's not a very interesting example, it's an example of real usage of Meta currently. So I'm going to start with it. Okay, so in the dialog system, we use AMR templates. Right now, it's not a very important part of the system, but still we have it, and this is exactly the part which was originally written, maybe not written, but which used Opencog Classic and its pattern matching techniques. So AMRs represent, just a little context, AMRs represent a sort of a semantic structure of sentences, and we introduced AMR templates as an extension of AMRs, which can have sets of AMR graphs. So you can construct a graph which element will be a set of other possible graphs, as well as variables. So the idea is that if a sentence, an AMR graph of a sentence can be matched against such an AMR template, then we can extract groundings or bindings for variables and do something with them for goal-oriented dialogues and so on. So this is exactly a graph pattern matching problem, but graphs are quite specific in this case. And when we did this with Opencog Classic, we didn't find a good way to match these graphs out of the box. So we used a Python code which wraps concrete queries to AMR graphs stored in atom space. And it looked like this. So if we want to extract a template which is associated with some context, we construct a query with some variables, and we use getlink, which performs pattern matching over this expression or subgraph with some variables. And what we have done with Meta, while in the case of Meta, it would be very nice to actually, it's very close to how Meta looks like, and it would be very nice to have this AMRs as AMR templates as purely Meta expressions, but because we are working with a system which is being used, so we decided to directly map the way of how Opencog Classic was used to Meta. And in this case, we have absolutely the same set of helper functions, but instead of constructing Opencog Classic atomize queries, we are constructing them in Meta. It looks a little bit more concise, and actually in this example we also got use of unification or two-sided pattern matching, because AMR templates have variables, and when you want to perform an atom space query, you need to do both things, to bind variables in the query and to bind the variables in expressions stored in the atom space. So this is one particular example where our modified approach to static pattern matching was really helpful. So you can match these expressions right away without the necessity to first retrieve the whole expression, to extract variables from it, and to sort of manually or additionally bind the variables in the extract expressions. I'm not sure what the status of Opencog Classic right now. Maybe it's already capable of doing this, but back then, it was like 3 years ago, it was not possible to do out of the box, while in Meta it is doable. Unfortunately, as I mentioned, because it's a live system which is under use with different demonstrations and so on, we didn't go far enough to refactor all this code to have everything in pure meta, and it would be good and cool, but because it's not a very important component, so we stopped here with it. But what I wanted to emphasize is that meta in this maybe not too AGI-ish or extensive use case is being used not precisely in production, but in live systems, and it works with not worse performance than Opencog Classic. And we continue to make use of meta in the dialog system, replacing dialog states with meta expressions and putting them into atom space. And once again, it was not quite convenient with Opencog Classic because its ideology of static atoms. It was possible, but just not convenient or not efficient. And having dialog states which are mutable is quite convenient in meta, and at the same time they are matchable. However, this example is not the one which could attract open source developers because it relies on a lot of legacy code and it uses meta in a restricted way, although it is possible and hopefully it will be done at some moment of time. It is possible to make a much deeper usage of meta. So what would be nice to have as more advanced examples? Of course, when we are talking about some real-world applications, we need to interact with additional pieces of software and so on. There are, of course, more advanced uses of meta for developing Hyperon. I mean PLN pattern miner, but these are not applications, but these are parts of Hyperon to be developed in meta and only then to be used. There is work on Flybase portion to the distributed atom space and to be used in meta, and this is a good possible practical or real world usage of meta, but it's also a little bit specific. So the first thing which I would also like to add that this is an example of using meta from other languages, and of course when we have more such examples we may make this usage more convenient and flawless. And another one example is Minecraft agents. Porting Minecraft agents to meta was a little bit deprioritized because of different aspects, in particular because of rocketing of large language models and so on, but we are also working on it, and it's one more example of usefulness of meta in the course of development in another language like Python, because Minecraft agents they are more convenient to write in Java or Python, just because you have already worked in APIs there, and there is of course a lot of issues with missing libraries for socket connections or whatever. And this, of course, should also be done step by step to be introduced to Meta when it is ready. But right now, of course, it's more convenient to write Minecraft agents, say in Python with meta usage for retrieval from ontologies, for planning, and so on. But this is not a product yet, and it's maybe a little bit more involved example than we would like to have for attracting open source developers. So I would like to talk a little bit about integrating Meta with neural networks and other subsymbolic systems. And I would like to show the usage of extensions of Meta with Python libraries. So there is a mechanism for this, which may make Meta programs much more usable for different real-world applications. So this is a sandbox example of extending Meta with NumPy library from Python. And it's not in the standard library, maybe it will be someday, but actually extending Meta is quite simple. So you need to write a bunch of tokens to be added to the parser, and these tokens in the course of parsing they create atoms, grounded atoms, which can be executed in the follow-up code. So in this case we have a token for creating NumPy vectors or NumPy arrays. These are actually grounded functions, so they are called not in the course of parsing, but it's just replaced with the corresponding grounded function, which turns its arguments into a NumPy array and wrap-ups it into a grounded atom, which can be used in the follow-up program. So we can use such functions in normal meta expressions, and if we run this, then it will produce the corresponding output. So we have x, it's a token, but in any case, it has x bound to the vector 1, 2, 3, and we have a pure meta function which adds 1 to a given vector, delegating this to a grounded function imported by the extension provided in this call. So we can construct normal meta expressions without any problems. We can compare vectors. We can add vectors to matrices and so on, and it's done in a very simple and straightforward way. But besides just wrapping grounded functions, we can do something more interesting. In particular, we can extend the idea of matching with custom matching procedures. And in this extension, there is quite simple yet useful matching operation for NumPy arrays. And for example, we can with this implementation we can pattern match an NP array against some patterns in meta and get some results. So in this case, the pattern, the array can be matched against this pattern. So what we got here is I wonder. Sorry. So it doesn't work. So for some reason. Yeah, it works here. It pattern matches NP vector against X, and X is exactly the same NP vector. I'm not precisely sure why it doesn't return the result here. Maybe something has changed. In the latest updates, I need to check this out. Okay, but in any case, it at least works in the latest case. So it pattern matches this vector against the array and returns the right result. Sorry. Okay, we will not waste time to see why the result is not correct in this case, unfortunately. So yeah, meta is still not too stable. I would like, well, it's an example with NumPy, but in the same way we can wrap up TensorFlow or PyTorch tensors and manipulate with them. So if things work right, then you may have a pattern matcher against tensors and to extract some components of these tensors using corresponding meta expressions. So it's a step forward from just module networks which construct networks in the course of symbolic manipulations, because besides the construction operator, you will have a deconstruction operator, and we used ordinary module networks with Opencog Classic for visual question answering and grounded, visually grounded reasoning for street scene analysis. But in meta with such deconstruction operators, it might be possible to come up with some additional ideas of how to how to use yeah, interestingly. So in this case, it didn't work because it was actually it actually worked. The problem is that for some reason it doesn't substitute the variables. So it because it has two components, the highest level tensor has two components. It was pattern matched against this one, and it says that it should add x to y2. This is right, but for some reason it doesn't substitute the result. So maybe some latest changes in the case separation or in bindings made this example not completely working. So it nearly works, but it doesn't for some reason substitute these results. And if we change the shape of this tensor, then yeah, it returns B, because in this case it matches against this pattern and returns B, but this B is also for some reason matched bound to the concrete value. Okay, we will fix a little bit later. So I believe that it is possible to create a library on top of say PyTorch to manipulate tensors in an interesting way, to make it possible to deal with module networks or something else, or maybe it can be used for assembling some pipelines, like Ben mentioned, the idea of taking a stable diffusion pipeline with all this its variations, with control net, with the image to image, with in-painting, and so on, and describe components of this pipeline in a formal sort of formal specification, sort of formal model card. And in this case, it might be possible to automatically assemble such pipelines based on this specification in Meta. So this is one possible direction of creating a lightweight library which wraps up PyTorch tensors and allows users, programmers to do something cool with them without the necessity to code everything manually, like automatic assemblance, automatic deconstruction of PyTorch models, and so on. There is the request for this actually in the machine learning community. That's why safe tensors appear, which help to load models automatically without the necessity to have a class in Python which has corresponding fields. So it's the topic for discussion to what extent we want to go to this direction. Another possible direction is interesting in the current context, in the current hype in LLMs. So let's have another extension of Meta, and this extension will have actually only one grounded function, which creates a sort of space, and we can use traditional Meta functions to place atoms in this space. And then we would like to query the content of this space, and okay, so we place some information about the user, and we may want to query with the use of ordinary match function what is the name of this user. And it works. So we have a query in a very different form than in a traditional meta. We can ask how old is William. Yeah, and it also retrieves the necessary information. And we can even ask how old is Mike, who is younger than Nick, who is older than William. Yeah, and it works. So 26 plus 3 minus 5 is 24. So it's not the work done by Meta itself. It's actually a very simple wrapper to GPT-3, which actually it's not precisely the neural space which we have been discussing with Ben and others, but it's just a lightweight example of how we can have a different type of space. So what I envision when I am talking about neural space is something much more deeply integrated to hypergraph atom space. It can be sort of embedding, so transformers specifically trained on atom spaces, so it's not just available pre-trained large language model which we play with using different prompt engineering tricks. But actually this API, I mean, the possibility to create and match spaces in Meta, it literally became available yesterday. So I just spent an hour or two preparing this example. It was a long-term refactoring with space API introduction and so on, and different steps of this refactoring were made at different moments of time, but the final API became available only like a day ago. So what we can have? We can have different types of spaces, and this is just one example. For the meta interpreter, it doesn't matter what is under the hood if API works. So it can be a distributed atom space. It can be restricted in terms of what it allows to do, space connected to raw length via compilation or whatever. So it's the idea of one of the ideas of Meta is that it can be extendable. And what is fun is, of course, that you can easily add some meta. Yeah, it works. So you can easily add some meta expressions on top of it. And if we are talking about not a grand vision of neural symbolic integration in terms of AGI, but if we are talking about just a middle level example of meta usage for attracting open source developers, then it can be the case. So I don't think that it's a path to AGI. It's just a shallow way to use meta together with large language model. But you can do much funnier things than just this. we performed simple experiments, and it seems that current LLMs can figure out if they don't know something. And in this case, this information can be stored not in the neural space, which is just put as a prompt to the large language network, but if we have a large atom space, graphical space, which cannot be directly put into the prompt because it's just too large, and if LLM can figure out that in order to answer some question it doesn't know something, then we can construct such a prompt that in this cases it will construct a meta expression or some formal expression which can be easily converted to a meta query, and it can be executed. So we can just have a function which calls, which executes an external LLM, and this LLM can return not just bindings, like in the case of matching pattern in a neural kind of neural space. It can return another meta expression to be evaluated, and in this case they can go back and forth. So some meta functions will make calls to LLMs, and LLMs will make calls to meta, and the interpreter will just change them. So this is one possible direction. It's not a very big deal in terms of the value it adds to the already available tools, because there are different solutions and libraries like LangChain and so on, which shows how to force LLMs or GPTs to make SQL queries to the external database, or how to make SparkQL queries to Wikidata. So it's not precisely novel, but if we are talking, for example, about LangChain, it's agents, it's prompts which are chained together. They are not composable. So you can make an agent which queries Wikidata, but it's not possible out of the box without some additional prompt engineering to compose it with other calls, with other prompt templates to GPT. And there is also no way to embed this out of the box into the code in Python or whatever. There was another project in which different calls to GPT with different prompts were wrapped up into Python functions. So you can write in Python implicitly, or maybe not implicitly, executing GPT with certain prompts, and it looked like a normal programming language case, but actually GPT worked under the hood. In the case of Meta, it's much more natural to do both these things simultaneously. So it's quite simple to construct interpretable meta expressions because well, how to put it, any expression in meta is actually more or less valid up to types and syntax, while if you ask to generate GPT a piece of Python code, it will be more difficult to use it in a certain context. So as I will repeat, as a local example, or not AGI example of how to use Meta, it might be interesting to develop a library with composable calls to GPT, and with the possibility to get back meta expressions from it, and make a talk between a meta program which can store knowledge in its own space with GPT, which also has a sort of knowledge stored its in own space and in its weights. There are, of course, other possibilities of what middle-level examples to create, which can attract open source software developers, but it's difficult to cover them all. So my intention was both to show 2 or 3 examples of more sort of real-world meta usage, not just pure meta scripts, and to show such possibilities of extending meta with different matching functions. So these matching functions can be attached to corresponding atoms, like NumPy arrays, or it can be attached to the space itself, and there are different possibilities of amusing use cases for this. So I guess I will stop at this point, and thanks for attention.
Then select the model.
Yeah, thank you.
Unfortunately,
It's not there yet, huh?
It's not there yet.
Oh, we unplugged it. Oh, no. Alexa, can you hear us?
Yes.
Yeah, I think it might be going. Okay, great, excellent. So Unfortunately, there's going to be a delay between, very add-on.
Oh, you showed the YouTube, so the 20-second delay between question and answer. That's better just to go back to the
Let's go back to,
effective audio.
to this. Alexa,
The whole thing?
All right, we're just having some audio stuff that was happening, but I think we've got it resolved
Yeah.
now.
Okay, I'll check. You can.
Okay, great. Did we have questions?
Thanks a lot, Alexei. We had some audio complexities on site in Stockholm, but fortunately, the code you were showing was quite clear. So I think it came out fine, and the audio on YouTube was fine. So does anyone in the room here in Stockholm have any questions or comments for Alexei? No has something.
Yeah, hi, Alexei. Yeah, on the last piece of code you were showing with the queries in natural language, the last query, so the variable x had parentheses around it. And I think the reason is because there was a calculation going on, but could you either show a little bit more what's happening beneath the surface, because like I don't understand why how the calculation went through the query, and that's kind of a little confusing. So that would be
it indeed. Sorry, can you mute on your side? Okay.
you
Is it possible to mute your notebook?
right. So can you hear me?
Yes. Okay, so now it's muted. Thanks. So yes, thanks, Neil, for asking. And indeed, this example is intentionally confusing. As I very briefly mentioned, all the sort of calculations are being done on the side of ChatGPT, so it's not precisely the achievement of Meta, but it's a showcase of using external spaces which can add some value to Meta. Actually, I can also say that it's not. It might not be very good. Okay, so it doesn't work without parentheses, or we can ask another question like what is Mike age, and it will return some stupid result. And what is happening under the hood is a construction of a very simple query to the ChatGPT. So I can show you this query in this case, like so this is the actual query. It just inserts the content of this sort of neural space into the prompt, and it has some instructions in what form to provide the answer. And if we consider what it outputs, I mean, what ChatGPT outputs in this case, it's simply this one, because it failed to reason over it. Sometimes it's a task of prompt engineering, and I just didn't have time and a goal to do this carefully, just to make a few examples working. This is the response of ChatGPT in the case of this query. So it's not just X18, but it kind of reasons by itself. It sums up 26 and 3, it subtracts 5 from 29, and the result is correct, but it far from always correct in different cases. And we can ask some questions about something it doesn't know, like what X is a father name or something like this. Yeah, and it will provide a good answer, but this good answer just is not parsed. It is turned into I guess symbol, meta symbol with a very long name. So it actually grounds X or binds X to the symbol. The information provided does not include the father's name. With more careful prompt engineering, it is possible to turn it into the meta expression, which will be evaluated further, and possibly if we have father's name in another space, then we can query the space and return this name and put it to the neural or GPT space for it to know this information and to answer further questions. So it's possible to do different funny things with it, but I just didn't have time and a goal to do it yesterday. So I hope it's more clear now what is happening under the hood.
It's very much, Alexei. Any other? We had a question from the channel. Somebody was saying that the granularity in your presentation, and I missed the part they may have been referring to, but is the granularity is symbolic, not sub-symbolic. Is that right?
Well, I'm not sure what granularity is being referred to, actually. Maybe it's the same question as Neil has asked, because I'm not sure what else can be meant by symbolic or sub-symbolic in this case. But all the code in Meta itself is symbolic, yeah. But grounded symbols and functions are sub-symbolic.
Cool. Thank you very much. And then we had another question: is Meta like TensorFlow or PyTorch?
No, it's very different, I guess. Although there are some similarities, probably because, say, TensorFlow or PyTorch, they also construct graphs over tensors, and there is a data flow over this graph, and actually we can, in principle, go much more beyond the current level of integration of Meta with, say, PyTorch, and replace PyTorch graphs with Meta expressions, and to have only the lowest level tensors as grounded atoms composed into these expressions. But well, the main point of TensorFlow and the PyTorch is to have automatic differentiation, and we apparently don't want to re-implement this. So I wouldn't argue for going too deep, and we could turn Meta into something like PyTorch, but I don't see why we should do this. There are some similarities, but such similarities can be found in different platforms, frameworks, and so on.
Alexei, any other questions from the room for Alexei?
Sorry.
Just asking if there's any other questions from the room. Okay, cool. Thank you very much. That was a spectacular update. Thank you very much, Alexei. I think we'll pop to lunch. We're about 20 minutes behind schedule there, and then we'll come back for Greg right after lunch. So we'll meet everybody back here in an hour. Okay, fantastic. Thank you, Alexei.
Thanks.
Okay. Oh, apparently. Apparently I have to relaunch Zoom because I had to. So. Sure. Just 1 second. I just need to make sure that Zoom launches. Ah. Well, while Zoom is doing its thing. Good afternoon, noon. I guess it was the room after all. So thanks to Ben and the SingularityNET for inviting me. If you don't know me, I'm Greg Meredith. I've done a few things. I was the president and founder of RChain Cooperative. Before that, I did BizTalk process orchestration for Microsoft, and this is just a long series of sort of engagements to try to get to a model of concurrent computation that I think will both be accessible to the people in general, but also safe and robust. Hang on 1 second, I have to rejoin this Zoom room. Let's see if this works now. Okay. All right. Okay, now let's see if I can do a share screen. Okay, for today's talk, I'm going to kind of blend a couple of different presentations. Mostly I'd like to talk technical, but in order for the technical talk to be motivated and make sense, I'm going to give a little bit of an overview, which I gave about a week ago to the Federal Blockchain Working Group at their invitation. So I will launch into that just to kind of, let me see here. I think slideshow, is that, how's that look? Is that visible? Okay, good. Okay, so I'll be talking about the operational semantics of Meta and why you would want to do that and how that relates to AI and a few other things like blockchain. In case you don't know much about RChain, I'll kind of talk a little bit about that just to set the stage. The RChain code base is still open source. It was always open source, and a bunch of groups have picked up the RChain code base to provide the basis for their projects. There's Ronix, which is going into blockchain and gaming. There's Concursus and Row Vision, but Firefly, which is my company, is really the successor to RChain. And one question is, what makes this technology so popular and that so many projects are picking it up? And there are 4 basic benefits. It's scalable, storable, searchable, and secure. What do we mean by that? So RChain is arguably the most scalable blockchain on the planet. And what do we mean specifically by that? So most people when they give you a scalability metric, they give you one number, which is TPS. But that's not what scalability means and is not what we have meant by scalability for the last 50 years in terms of software systems. What we mean when we talk about scalability is that when you add hardware, when you add more physical threads, the system gives you more performance, and in particular, often more throughput. So for us, as of January of 2021, we were getting about 1,000 transactions per second per node in the network per CPU. So that means you could do actual network resource planning. If your community needs 10,000 transactions per second to support you, then you need to roll out a network of at least 10 nodes and each of those nodes needs 10 CPUs. That's 10,000 transactions per second. If your community needs 100,000 transactions per second, you need at least 100 nodes in your network, each node having 100 CPUs. So the point is, and if you look at how that relates to hardware trends, I mean, the old Moore's law is over, right? Since about 2005. The new Moore's law is that hardware vendors are providing more physical threads per cubic centimeter at lower power consumption and lower cost about every 18 months. So that's that. So if your software architecture doesn't eat physical threads and turn that into performance, you're already dead. You may not know it, but that is really the reality. So that's what we mean by scalability. And because of that scalability, we can store data directly on chain. So when we launched testnet 0, we demonstrated putting audio data on chain and delivering it back in real time. As of August of 2022, we demonstrated putting video data directly on chain and delivering it back in real time. Rolang, so you mentioned NoSQL databases. Rolang in 6, count them 6 term constructors or program constructors. We give you a concurrent query language, transactional query language that gives you the best of SQL and NoSQL. And so this is important because when you think about blockchain architectures in today's world, they have missed the point in so many different ways. One of the things is that search is what created the global economy. So if you think about when the culture that happened when ordinary citizens could, on a 24/7 basis on their mobile devices and laptops and desktops, could find employees, they could find employment, they could find reviews, analysis, weather reports, etc. That's when the global economy became a reality. But if you compare that to where blockchains are today, so like OpenSea's architecture puts the actual digital assets on a non-searchable storage mechanism, IPFS, behind a non-searchable blockchain, Ethereum. And so when you talk to artists who launch NFTs, the first thing they ask is, how do people find my work? It's literally a step backwards from what created the global economy. By comparison, Rolang on our chain and the Firefly architecture is a transactional query language. You can literally search the data that you put into the chain. And it doesn't help if your blockchain platform leaks security information, like with the DAO bug, or allows for unauthorized transactions, like with the DAO bug. So we provide another mechanism for catching those kinds of safety, liveness, and security errors, which we'll talk about. But that's sort of, in a nutshell, what our chain and Firefly is all about. So what does all this have to do with AI? Again, this talk was directed at the Federal Blockchain Working Group, and they're not a bunch of AI geeks, so it had to be watered down. But roughly speaking, the way I described SingularityNET to them was was of the things that SNet has understood is that AGI is not equal to LLMs. So this was a revelation to the Federal Blockchain Working Group, and I sort of suggested that AGI might be LLMs plus some symbolic reasoning and a few other things. So that was something that when helped them understand what SNet and in particular Meta is about. And the way I described Meta for them was that it's SingularityNet's language for expressing symbolic reasoning and gluing components together. And I think if you look at Alexi's talk earlier, that was precisely what he was doing, right? He was doing some symbolic reasoning and gluing various components together, treating those components as if they were spaces. And I think like many companies in adjacent spaces, you know, SNET got dragged kicking and screaming into language design. It's language design is its own thing. It's a hard thing. You know, it's the job is never done and nobody ever gets it right. And in particular, you know, the folks at Hyperon really know AI. That's obvious. And in order to scale Hyperon and Meta in particular, that involves concurrency, and concurrency is scary. And what do I mean by scary? I mean that if you go look at the data on this, you can give concurrency problems to seasoned experts who have solved the problems before and they get it wrong. Concurrent programming is much harder than sequential programming, and it is so easy to screw things up. Rolang provides a model which overcomes some of that, and then provides a notion of typing which helps you go the rest of the way. Again, it's never going to tame the bugbear that is concurrency, but it helps you kind of bridge that gap. So one of the things that we're doing for SingularityNET is to translate Meta, compile it into Rolang. And so that allows us to identify where the concurrent execution opportunities are, and to provide mechanisms to help make those safe. Now, to ensure that our translation of Meta into Rolang is correct, we actually need to know what Meta does. So Meta itself, they have 2 reference implementations, but not a proper spec. And like I said, language design is hard. It is hard to produce a spec for a language. This is a non-trivial effort. So what we did was to provide an operational semantics for Meta, so that we could do our job of correctly compiling Meta to Rolang. Right, that was step number 1. Actually, step 0, right? Is just to make sure, hey, this is what we think your language does. And actually, I will switch over to the other presentation in just a moment. But there's something kind of unprecedented in software. Anyone who's actually worked in software knows. So one of the co-authors on the paper, he took the operational semantics and forgot about all the Meta implementations, said, I'm going to ignore all of that, and just did a Scala implementation of the math in the paper, and then ran the Meta tests against that software. And they all worked, except for one. And the one that didn't work revealed something interesting about Meta, which we'll talk about a little bit later. So I'm going to stop here for just a second, take a breath, take a pause, and check in and see any questions. Is this making sense? Is this leaving people in the dark? Okay. All right. All right. So now let me switch over to a different presentation, so I can talk a little bit about what that operational semantics is. There we go. Huh, that's not quite what I wanted. That's interesting. Okay. All right, well, this is strange. It's not letting me. Okay, we may have to, there we go, finally. Oh, there's that. We might have to live with a slightly suboptimal screen. Apologies for that. So in order to talk about an operational semantics in a way that I think might make sense, especially to folks in the AI world, is just to observe that there's actually a remarkable degree of agreement and consensus on what it means to present a dynamical system that can compute. So basically, if you're from a physics background or a math background, a presentation of that form is, what are your states and what are your laws of motion? That's it. That's all there is. Now, it turns out that states have an algebra to them. We don't have to go in too much into what that algebra might be. Typically, in computer science, that algebra is a monad, and we know it's an algebra of the monad because there are typically some equations on the states that erase differences that might be present syntactically, but that are not material for execution. And then in the computer science world, those laws of motions are typically expressed as some form of rewrite. We can talk about lots of different models of computation, but they all end up, well, a majority of them end up being captured as some form of rewrite. So in the computer science world, the gold standard since Robin Milner's paper, Functions as Processes, is you have a grammar that specifies an abstract syntax of states. You have some structural equivalence that specifies equations on the syntax of states, erasing syntactic differences that make no difference in terms of the semantics of the language, and then some rewrite rules that specify how systems evolve from state to state. So let me give a couple of examples. And these examples are nice for several different reasons. This one is the old workhorse. It's the lambda calculus. Hopefully everyone here is familiar with that. If you're not familiar with the lambda calculus, let me know. Okay, all right, let me walk through that then. So the lambda calculus was developed by Alonzo Church and Haskell Curry. Alan Turing worked with Curry on the lambda calculus. This line here is the grammar, and the way you read that is it says that programs, which we're going to use m and n to range over, are of the form, they're either variables or they're lambda abstractions. So it's a program waiting for some input, which we're going to call x, or an application of a program to some data. And then there's an equivalence which erases some syntactic differences on states that we don't care about. So here, I'm not introducing the notion of free names, but lambda here is a binder. So it says I'm waiting for some information, and that binder, things that are not under a binder are considered free. If you don't know this, go look up Baron-Drake or any of a number of different tutorials. But what this equation here says is it's called alpha equivalence. And basically it says that, you know, the variable I'm using for my function, really, I don't care what its name is, right? I can change lambda x.m to lambda y.m as long as everywhere that x is mentioned in m, I go and replace it by y. And this is under an assumption that I haven't accidentally captured y, right? So that's what this equation is, and it's called alpha equivalence. And then there's one rewrite rule for the lambda calculus, and it says if I apply a function to its argument, then everywhere in the body of the function, I go and replace that argument with the value that I got for the argument. That rewrite rule is called beta reduction, and lo and behold, this little tiny system is sufficient to capture all of sequential computation. To capture concurrent computation, this is currently the best model we've got for a number of reasons. I developed it as a result of finding a small lacuna in Robin Milner's pi calculus, for which he got the Turing Award. This is a tiny little problem with Robin's calculus, which you can fix rather quickly if you analyze it carefully. And again, just like the lambda calculus, it fits in a tiny portion of the page. And the way we read this is programs or processes in this case, we're going to use P and Q to range over those. And they're of the form either the stopped process, which does nothing, or the process which is waiting at X for some information Y, and then will become a program P, or the process that is sending on X some process Q, or the parallel composition of P and Q, or take X and dereference it and turn that into a process. Now, the reason we can do that is because all X's, so you think of these as channels, right? So this is waiting on a channel for some data. This is sending on a channel some data. But channels, this is the one little mind twist for the row calculus. Channels are the codes or the quotes of processes. So that's the only trick. And then the equations, the little bit more sophisticated than you've got here. Basically, these equations say that processes, along with parallel composition and zero, form a commutative monoid, and that the for comprehension is this variable here is a binder, and so it is subject to alpha equivalence. So that's all the equations, and then there are 3 rewrite rules here. What we're saying is that when some process that's waiting at X for Y meets up with a process that is sending on X, then we take the code of this process here and we replace it. This should have been Y, not X, sorry. Then we take the code of Q and put that in for Y everywhere it occurs in P. And then these are just, this says that if P will reduce or evaluate to P prime, then P in parallel with Q will reduce or evaluate to P prime in parallel with Q. So while this rule says that the vertical bar is about interaction, this one says it's also about isolation. So P can make progress on its own, and it can make progress in parallel with Q. And then this one says that all reduction is happening at the level of equivalence classes over these equations. So if P is structurally equivalent to P prime and P prime reduces to Q prime, and Q prime is structurally equivalent to Q, then P reduces to Q. That's what's being said there. And so those are 2 examples of an operational semantics. This one here is what's at the heart of our chain and why our chain scales the way it does, because it has a model of concurrent computation that allows us to detect when transactions step on each other's toes. So we can detect that both syntactically and at runtime. And as a result, if they step on each other's toes, we know that they have to be sequentialized. If they don't step on each other's toes, they can be run at the same time. And since they can be run at the same time, we can assign them to different physical threads. And that's why our chain scales. You can just see it in the syntax. So now let's talk a little bit about meta and how this plays out for meta. So so the states for meta are a little bit different. The way I codified this for the meta language is to treat it as a register machine. So if you dig into Alexei and Vitaly's examples, you'll see that they introduce operators like bang, which is to inject a query into the system, and they do add atom, things like that to various spaces. So that has to do with these different registers. So this is the input register to this register machine. It can be thought of as an atom space itself. It's where an agent that is interacting with the meta interpreter or the meta code base is going to input, like to effect a query, right? So the bang operator that you saw on the screen is placing things into this register. The K register is another atom space. It's the knowledge base. It's where we put a bunch of rewrite rules. The working register is where the results of having done some rewrites go. So this allows the interaction between the K register and the W register is what allows for chaining. So we can keep rewriting on rewriting on rewriting. So that's what that register is for. And the output register is when I've got something in the working register that is insensitive to any rewrites, there's no more action that it can participate in, then it can be moved over into the output register. So we can think of this as it's somewhere between, you know, Lambda and Turing machines, right? You can think of this as a little bit like an SECD machine and a little bit like a Turing machine. The question is, what is a space? So what are these different registers? So spaces are, they're multi-sets of atoms, at least in this model. There could be other things, but at least in the way we're thinking about them now, they are multi-sets of atoms. So now I have to tell you what an atom is. And you'll see that I'm literally following the recipe that we saw in those other examples, right? So the recipe here, I'm saying that an atom is either some ground, which could be a bool, a string, an int, or some built-in functions, or a variable like x, y, z, etc., or open round brace, and then you have an atom, and then possibly an empty list of one or more atoms after the round brace, and then in the examples before, they did not have a syntactic representation for spaces. I strongly urge and argue that there should be a syntactic representation for spaces themselves. So you should be able to see the structure of the space. But that's effectively what an atom is. So a multi-set of these things will land in each of these registers. And then these rules here are going to tell us how we change from one state like this to another state like this. So I'm going to stop here again, take a breath, a pause, and see if there are any questions. People following along? Did that make sense? Okay, all right. Okay, so I won't go into all of these rules. I'm just going to dive into one of them so you can see what it does, how it works. But these rules are very much cut of the same cloth as these rules. So here, where I've got this double arrow, that's the same as doing this stacked over top of this line. So you could rewrite this rule as all of this double arrow, this. But we use this vertical notation as opposed to the horizontal notation because it saves us space, right? It saves us horizontal space. So that's why this format for expressing these kinds of rewrite rules is called structured operational semantics. It was developed by Gordon Plotkin back in the 80s, and lots of people use this. It's, again, sort of the gold standard for writing down operational semantics. We've taken a little bit of liberties with that format, but by and large, this conforms to the structured operational semantics format. So what does this rule say? So if we look at the bottom for a moment, it says that if I have some, and just for purposes of discussion, I'm going to ignore this K around the T prime for just a minute. And likewise, I'm going to ignore these Ks here. So let's pretend that they're not there just for a moment, and then we'll put them back in and talk about why they're there and what that reveals about certain things about meta information flow. Okay, so what this says is if I have some T prime that is added to some input space. And I don't know anything else about these other registers just yet. This stuff will give me information about these other registers. But if I have some T prime that is added to the input register, then I'm going to go to a new state in which T prime has been taken off the register. It looks like we haven't changed K at all. But I've got a bunch of new things added to the working register, and it looks like the output register has not changed. So that's the basic shape of this rule. Now, where do these U's and these sigmas come from? So the idea is that when we look inside K, we find it divided into 2 bits. There's a part K prime, which is insensitive to T prime. Now, what we mean by that is this part, it might mention some rewrite rules, but the heads of those rewrite rules do not unify with T prime. That's all. And then there's the other part where I have a bunch of rewrite rules all of whose heads unify with T prime. And for each one of those rewrite rules, let's say the ith rule of this collection of rewrite rules, when you unify that with T prime, you get the substitution sigma I. So what we're really doing is we're triggering all of these rewrite rules and we're putting them all into the working register. That's what this rule says. And you can see that it gives you potential concurrency, right? Because you get, if you think of any one of these rewrite rules as affecting a thread of operation, then what will happen is each one of these threads is potentially going to run forward. You're frowning. Do I have a question? Okay. So this is the query rule, and the chain rule is very, very similar to the query rule, except that instead of working on the K register and the I register, it's working on the W register, right? So it allows us to if there's something inside of W that triggers rewrites, then that will then cause adding more stuff to the W register. So it's basically just the same as this, but it allows you to chain queries end on end. That's what's going on with this rule. And if you're comfortable with that one, we'll do one more and then we'll move on. So the transform rule works kind of dually to query and chain. So what it's saying is that we've got the transform atom inside the input register, and if there's anything in here in the K register that that unifies with T, then we're going to put U with the substitution applied over into the working register. So you can see this is slightly here the transform is running over the knowledge base. Here we have the knowledge base running over the rewrites. This is yeah. I'm not explaining it very well, but you can see how here's a kind of rewrite coming in on the input register, whereas here the rewrites are over in the knowledge base in the K register. Hopefully that makes it a little clearer. It's not just it can literally rewrite anything inside of the knowledge base. Yeah. Now let's go back and put these Ks back in. So what we noticed was originally I didn't have the Ks in here, and there was one example that didn't work. So we analyzed the example, and I realized, oh, there's information that needs, we need to take into account that we might have matches that go deeper into the term, and so that's what this allows. It allows for matches somewhere inside a term, but notice that wherever that match happens inside the term, there's a substitution that happens in that place and in that place only. That's the way this rule works. But this doesn't let the frog example from the test suite go through. And the only thing that will let the frog example from the test suite go through is if you take this substitution and you put it on the outside of this context. So that means that this substitution information is potentially leaking information throughout the context, right? So if there's a variable binding that gets created by T prime, it may wander up the syntax tree and affect the rest of the context where T happens. And that's potentially dangerous. So I'll talk about that danger in a situation that might look innocuous and innocent, and we'll see how it raises a whole bunch of problems. I'll give a simpler one, even simpler than frog. Yep. Yeah.
So, what is insensitive?
Insensitive means that T prime does not unify with the heads of any rewrites in K prime.
Oh.
Sure. Yeah, I said that, but I must have gone by. So just so you know, those rules are only about sort of the core constructs that make meta. But then there are built-in operations that every language needs to support, which we talked about when I introduced the syntax for atoms, right? So you need to support addition and multiplication, a bunch of ring structure that works for lots of different kinds of data types like bools and ints and strings and things like that. So there are also a bunch of built-in rules. We don't need to spend a lot of time on this, but it's typical to do this kind of thing, right? If you've ever implemented a Lisp interpreter, which like most undergrads have to do it at some point, then you have to deal with this kind of stuff as well. So let me give an example of just a very, very simple example of running the abstract machine. So suppose I have in my knowledge base that the symbol add XY gets rewritten to plus XY, where plus is that built-in piece of arithmetic. Then and the input register has add 1 to 1. Then by the query rule, I'll pop this out of the register because this unifies with the head of this rewrite, right? And the rest of the K space is empty. And so I will then apply the substitution of binding. This should have been a 1 and a 1, or yeah, let me fix it here. Sorry, that was a typo. Okay, so I'm adding 1 to 2. So the substitution, it will bind X to 1 and Y to 2. And so the rewrite then, when I apply that substitution to the consequence of the rewrite, then I get plus 1, 2. And then by the definition of plus, this will trigger the built-in definition, which gives me 3. We notice that 3 is no longer sensitive or engaged in any action in the knowledge base or the working space. And so I can apply the output rule and 3 goes to the output. So we started from this query and we get 3 out. And you can see how this is a thread of computation. And if I had other rewrites, then I would get potentially other threads of computation all happening at one time. So is this making sense so far? Rock and roll. Okay. If you want more detailed examples, one of the co-authors on the paper, Adam, who I was hoping would be here today, but I guess he isn't. Anyway, he, like I said, he did a Scala implementation of just the math in the paper, and that's in a GitHub repo called Formal Meta. If you're interested, come talk to me. I'll give you the link to the repo. But it was the one example we talked about, which led to the discovery of the security leak. So let's go over that. So consider that I have prepared a state that looks like this. So I've got some input register. I don't know what it is, but in the knowledge base, I have this rewrite where I rewrite f of x, y, z to h of g applied to x and y and g applied to y and z. So it's some kind of morphism gadget. Now suppose that a systems administrator introduces a higher order rewrite into the K register via add atom, which you've seen before in some of the examples. And so what is this higher order rewrite? So it takes all terms that look like this, f applied to x, y, z, rewritten to t, where t is some variable, and rewrites it to the rewrite, which takes f, x, y, z to t and log to some Google Drive x, y, and z. Right? So obviously we can see what's going to happen. So suppose some other user engages the system by querying f of my sensitive data, my other sensitive data, and my really sensitive data. Right? So now all this sensitive data, unbeknownst to the user, is going to be logged to the Google Drive up on the internet for anyone to see. But more generally, it means that isolation is not possible. You cannot know, and it is halting hard to determine whether meta programs are isolated. Right? So it is not halting hard to determine isolation in Rolang. That's sort of its claim to fame, is that we can syntactically determine isolation. Here, it is halting hard to determine when meta programs are isolated. So that means it's not just that you may run into issues like this behind a firewall. You couldn't ever use meta in this form in a decentralized setting. So you couldn't put it out there, you know, on the public side of a firewall and let it run with the semantics. Also, those are two issues that are security issues, but also it's a performance issue. Since we cannot determine that isolation, it's not possible to determine isolation. If there are any resources that might be shared, concurrent threads are going to have to lock down those resources while they're using them, which means that everybody is now going to be synchronized on all these locks. So you get almost no benefit from concurrency. So this is a really, really bad situation. Now it turns out that there are two fixes. So one fix is to don't let the substitution escape from the context. Don't do that. That's a bad idea. But it turns out that defeats a bunch of backchaining examples, like the frog example, which you can go find in the GitHub repo. And so instead, what you can do is you can introduce a notion of sealing. So we seal a syntactic scope. And if you're familiar with the pi calculus, sealing it's quite interesting, because what it does is it draws a boundary around a syntactic scope and a variable in that scope. But it doesn't bind to the variable. So in both lambda calculus and the pi calculus, the lambda abstraction is a scope mechanism. It says, you know, the x inside here means something different than the x outside of this scope. right? And in the pi calculus, if you say new x, it says x means something new, then any x outside of this scope, with some exceptions related to extrusion, which we don't have to go into. But in both of those cases, there's a binding for the variable. There's a binding semantics for the variable, whereas seal has nothing to do with binding, because you can still pattern match on a sealed variable. So it's quite strange. The sealed context it obeys all of the equational rules of the pi calculus new expression, but it doesn't bind the variable that is sealed inside the scope. So it's a new thing. It's cool. It's interesting, but it's something that is necessary if we want to have a mechanism by which we defeat this kind of security leak. So I'll stop there, take a breath. Any questions about that? That was new, interesting computer science. That didn't exist until we analyzed meta. I'm sorry, more than this one? I mean, this one gives you an infinite number of. Oh, sure. I didn't think it was necessary, but I can certainly give you an example. Oh. Yeah. I was for some reason it is not letting me. There we go. Okay, here we go. So here what we would do is we would say seal, and then we would take this rewrite here. Hello. Okay. X, Y, and Z, and do that. That's it. That fixes the problem. So then when this rewrite happens, the X, Y, and Z that are mentioned here will not be the same X, Y, and Z. So that's the fix. It's nothing magic, right? It's just introducing a piece of syntax that says we're drawing a big circle around this syntax tree, and yeah, that's it. So I want to mention a couple of other things. So since we've talked about the possibility of having these distributed computations, so lots of atom spaces, lots of meta interpreters attached to these atom spaces, and some of them are running in situations where they don't trust each other. So it turns out that even if you have a lovely blockchain underneath you, you still have to worry about denial of service attacks. So you could have the most spiffy blockchain underneath meta ever, but a bad actor can come along and say, hey, please compute all the digits of pi. And now that meta node is taken down. And furthermore, if that meta node is replicated, right? So depending on how you do your consensus, all of those nodes are now all going to be computing all the digits of pi. And so they're taken down. So the way Ethereum fixed this is to say, hey, let's have some kind of resource that must be spent in order to do a computation step, like the rules we talked about before, right? The query rule, the chain rule, transform rule, all those rules. You have a resource that has to be spent to take one of those steps, or to do some kind of a storage step. So anything that involves a computational step or a storage step is going to cost you a resource. Now, it turns out that there is a completely algorithmic way to take a rewrite system like this, an operational semantics like this, and introduce a resource. So what you're seeing here, I'm not going to go through it because the moral of the story is I turned a handle completely algorithmically and generated a version of the meta operational semantics that has gas in it, which prevents denial of service attacks, which then is one of the key mechanisms that you need in order to do a real honest to God decentralized distribution of SingularityNET nodes. Okay, now we're getting to the point. So like we just talked to, we've spent this entire time talking about meta and what meta does and how to make meta do some of the things that have been contemplated. But now we're at the point where we can talk about the translation to Rolang. Given the time, I will not go through these. I will not go through these translations by hand. I will note that what stands in for spaces in the meta formalism become channels in the row calculus. So for example, in the query rule, I walk up to the I register, which is a space, becomes a channel. So I go look for all of those things that match T, or T prime in this case, and then I'm going to do something with that. And eventually you'll notice that I'm going to put something which has a substitution applied to it, and that's because of this for binding right here, into the working register, which is a channel, right? So the Rolang idea of channels is a different way of thinking about spaces, and arguably it has some advantages, which we might want to explore over time. But anyway, the rest of this has to do with the operations of that rule, and then there's a recursive call to the evaluation. What is really important about this this translation is you'll note that we are translating states where a particular rule is applicable to a piece of Rolang code. And this is important because what we would like to do is to prove, right? Not just make a correct implementation, but to prove that this translation is correct, right? And so it turns out that there's a theorem in the paper, and I'll give you basically the proof sketch, but there's a notion of bisimulation that we can give to the rewrite system for meta, and Rolang has a notion of bisimulation that it comes with, and we can prove that two meta states will be bisimilar if and only if their translations to Rolang are bisimilar. And the basic trick is that we're making the translation out of the bisimulation relationship itself. So it's really correct by construction, and this is sort of the whole trick that has been used throughout RChain and Firefly, is to do everything correct by construction where you can. Now there are lots of places where we can't, right? If we're implementing on a language like Scala, well, Scala is full of warts. It's the language I love to hate. And Java is even wartier than that. And so they're weak links, you know, those things have not been proven correct. No, I don't. It's just hate. Turtles all the way down. But this methodology of correct by construction is one that I think is really vital. It's important. I do want to say that this work was not theoretical. It was not abstract. These tools and this approach to doing software development is, goodness gracious, 40 years old at a minimum. And if we hadn't done this, how would we have known whether we had delivered the goods, right? How would SingularityNET know that we delivered the goods, right? Like checking that our code did what Meta was supposed to do would just be a matter of throwing a bunch of tests at it, and you might get coverage, but yeah, coverage is not the same as a proof of correctness. So this is very practical, and in fact, let me share something else here. The compiler here, which I have written in Scala, it is now code complete, and we're in the process of making it more and more conformant to the operational semantics. But the code of the compiler exactly matches the translation in the paper. So to the point where when I'm all done with this, I will then go take the LaTeX from the paper and put it in as comments for the structure of the code. The Emacs buffer is too tiny for me to go through this with you line by line, but I more than would love if someone would go to the repo and do a comparison of the code against the translation. So there's just one more point to make here. So let me go back to that zoomed out presentation. I think here. So in general, the level that Firefly works at is at a level where we provide, you give us your model of computation, and we'll give you back a model of computation that will work in a decentralized setting and is safe. So we've talked a little bit about the model of computation where you've added gas to the model of computation, but there's another piece of the puzzle that you need to add in order for it to be safe, both inside the firewall and outside of the firewall, and that has to do with the spatial behavioral types. So the algorithm I talked about, where I took the meta operational semantics and converted it to an operational semantics with gas. So I call that the indecent algorithm for, you know, to inject it into a decentralized setting, indecent. But in reality, that algorithm is not a piece of innovation. That idea comes from forcing rewrite systems to terminate, which goes back to the 1960s. There's nothing magical about that idea. It's very, very old. However, the model which takes the algorithm which takes a model of computation and produces a version of that operational semantics with spatial behavioral types, that is new. And why do we need that? Well, here's a kind of picture. Yeah, okay. You can see this, but it's covered up by my Zoom stuff. So let's imagine that we've rolled out a Singularity network. And we've got some nodes in Dubai, we've got some nodes in Shanghai, we've got some nodes in Seattle, and some in London. And what the gas does is it prevents these bad actors from asking nodes to do things like calculate all the digits of pi. Because if that happens, then every one of these nodes eventually is going to be all calculating the digits of pi, and the whole network is ground to a halt. So my colleague Nash Foster sometimes says if they try to do an attack like that, they have to make everybody else in the network rich, right? Because they have to pay all these tokens to do that. So that's hostile fire, but it turns out that you also have friendly fire, and the friendly fire is when people leak information in smart contracts or meta programs that they have written themselves, right? So they didn't intend to take anything down, but they just made an error, right? And they might make all kinds of errors. So as soon as you have concurrent computation, like we saw, you can get situations where information is passing across concurrency boundaries, or two threads are hitting the same resource. There are all kinds of things that can go wrong in that setting. And without some kind of support, people inevitably get it wrong. And so what the operational semantics and logical form, OSLF, algorithm does is it protects against that kind of friendly fire. So it provides a bunch of syntactic, basically it's a type system, and I'm sure most of you are familiar with types, but these types don't just tell you how to wire an input to an output. They allow you to see into the structure of a program, like, does this structure have multiple threads? It allows you to see like things like, or have I sealed this context? You can see that from the OSLF. You can see things like deadlock. So this agent is going to send this message, but only if it receives this message. And this agent likewise is going to send this message, but only if it receives that message. So that's a deadly embrace. And you can type check those kinds of situations. So you can prevent them at compile time. So those are things that you can do with types in this setting that you can't do with Java types or Haskell types or Scala types. And we generate those kinds of types for your model of computation. So that's the two kinds of defenses that you would need to roll this out in a decentralized or distributed setting. So I'm going to stop there. Okay, what if I stop sharing the screen? And then just open it up for questions. Questions, comments, concerns, considerations? Yeah. Sure.
So the robustness with respect to decentralization is one interesting point, and it's relevant to the rollout of Hyperon on SingularityNET decentralized platform. Also, it's relevant to the potential use of Meta as a smart contract scripting language in the hypercycle blockchain, which is great. The concurrency aspect is another key aspect, which is what initially drew me to this, sort of because I could see for many of the things we want to do in Hyperon, like a map reduce type approach isn't quite good enough for making the run efficiently on the GPU. Like specifically, if you're doing a folds type operation that accumulates memory as you fold, so it's a chronomorphism of some sort, right? Then MapReduce doesn't deal well with that accumulating memory in terms of allowing you to distribute it. So I guess one thing I would like to time bomb. One thing I would like to understand better is sort of what's the class of algorithms that can be sort of straightforwardly made efficient on concurrent processing using the Rolang approach. I mean, you can't, obviously not everything can be made efficient concurrently, and not everything that theoretically could be made efficient concurrently could tractably be made efficient concurrently with this language. It was pretty clear to me that these memory accumulating folds can be, but I'm not sure which things can be or can't be, or what's the right way to think about that.
No, it's a great question. Let me, as a part of answering that, let me also mention that the execution model that sits underneath Rolang. So how does Rolang do what it's supposed to do? You can think of it as a kind of hash table. So it looks a lot like MongoDB, except there are two kinds of things that can occur on the other side of a key. So in Mongo, on the other side of a key, you put a value. And that's also the case in what we call RSpace. But we also put continuations. And so in that setting, if you attempt to put data at a key that has a continuation weighting, then all you do is hand the data to the continuation and off you go. And if you attempt to get data from a key that doesn't have data, then you stuff the continuation there. So that's the basic model. And so the class of algorithms where you get the most bang for buck in parallelism or concurrency in general, regardless of whether it's Rolang or anything else, is when you have no interaction, right? If it's embarrassingly parallel, and you know I can do this addition and that addition and that addition, and then none of those additions interact with each other, then you have no thread synchronization, and so you know basically you can make your highway as wide as you want, right? That's exactly right. So the sweet spot for Rolang has to do with how much lane changing you're doing. So if you think about it as a highway with n different lanes, and interaction is really when I cross lanes, right? So if everybody's crossing all the time, then everybody's synchronizing, and so you get no concurrency. So the sweet spot has to do with kind of sparseness of interaction, right? So interaction is crucial, it's essential, it's not some vector addition kind of thing. So it's necessary to do what you're doing, but it isn't, but it's sparse enough that you get some lanes that for some periods of time are running side by side. That's the way to think about it. I don't know how to, I can't give you another an abstract characterization, but I'm just trying to give you some intuitions about where the sweet spot is. Does that make sense? No, there's not a formal characterization that I know of. Yeah.
Interesting.
Yeah.
I guess there would probably be some sufficient but not necessary formal characterizations that could be interesting in an AI context to sort of know that if your AI algorithm matches some criteria,
Yeah.
you are going to get significant speed up. I mean, it would be, I mean, I can think of trivial ways to do that, but there's probably less trivial ways to do that. So I think it's an interesting direction, because for people developing AI algorithms on Hyperon, you'd like to be able to give them as concrete guidance as you can about what to do, so the thing will be accelerable by this pipeline.
Yeah, correct. That's exactly right. The spatial types will allow you to detect, oh, these things are actually autonomous, right?
Yeah, so what Neil says, that's what spatial types are for, and that's something that can be done using the capability to put special type systems on top of Meta. So you can define appropriate spatial type systems, and if you're using those in the implementation of your AI process, then from the nature of the type system, you could know that you're going to get some significant acceleration by using the Meta to Rolang pipeline.
Yeah, but in terms of a general characterization, you're going to have arithmetic over if guarded interactions, and that's very, very quickly halting hard. Yeah.
So a particular spatial type system is just, it's an example of a sufficient, but not
Correct.
necessary
Exactly. Yeah.
characterization of things that could be sped up well this way.
Yep.
I have a very specific question
Yeah.
on the Roland interpretation of meta.
Uh-huh.
So you said that each space corresponds to a channel, but if that is the case, don't we get like a lot of congestion?
Oh, yeah, that's a great question. That's a really good question. So the short answer is, think about a channel that you can divide easily into subchannels. And so what Roland does is it says, I've got a big fat channel, which is like, you know, X, right? And then we divide it into subchannels by pattern matching. So the X channel that matches this pattern, that's really a subchannel of X, right? And so it splits it up. Yeah.
Okay, so is the splitting, I would say, is the splitting corresponding to the splitting you've got from non-determinism?
You get,
Or
you get, no, that's also a very good question. So you get gross non-determinism when you're on separate channels. And then inside the for comprehension, you can have additional non-determinism when you use what we call a join. So I can join on lots of different patterns inside that for comprehension. And then that will also provide me a level of non-determinism. But if I just do a bunch of nested for comprehensions, then I have to, right? I have to, so for example, if I'm looking for a message that matches the number 5, I'm not going to bother with messages that don't have that shape, right? So I'll get some speed up, but every time I have to wait to get the 5 before I get to the next one, right? So nesting definitely slows you down, right? So yeah.
Thank you.
A great talk.
All right, thank you so much. I
Yeah,
appreciate it.
thanks a lot, Greg. So did Vitaly emerge? All right, so yeah, we've got a bunch more interesting stuff. So we have Vitaly is going to get sort of nitty gritty into meta interpreter again, and I think talk about his work building a minimal meta interpreter, just trying to come up with a small number of primitives that you can get meta language from. Then I think after that, Senna will talk about the distributed M space and where that is now. And he's been doing a bunch of testing of that on Flybase actually. And we just brought in someone new, Saulo Pinto, also in Brazil, who's helping just evaluate everything in Flybase and distributed M space. Be sure that's all working well. And then after those two more fairly brief talks, I think each one should be maybe a half hour. After these two brief talks on plumbing of meta, we'll take a break, and then we will return for the grand finale of PLN on Hyperon with Dr. Neil Geisweiler in 4 dimensions face to face, and then there are more dimensions. We just can't see them all that clearly. And then Hedra will come in from Northern Virginia and talk a bit more about some of the PLN stuff being done. And yeah, that's I guess PLN is the first of our sort of serious AI algorithms that we're putting into Meta, but Kasim is going to start shortly on putting Atom Space Moses into Meta, and after these guys have worked out all the kinks, then Matt and I will do eCan once everything is mature and it's gotten easy for us. So, but is Vitaly available now? All right, and
Yep.
otherwise we could.
Yep.
All right. So we got Vitaly Bogdanov straight out of St. Petersburg, and he is the lead developer of the primary meta interpreter. So him and Alexei have been sort of developing meta from the beginning.
Yeah, I hope my screen can be.
It's loading here right now. I still see a loading screen, but next year in the metaverse, right? Vitaly, if you want to send me your slide deck, I will play it from here and you can talk through it and just let me know when to switch.
Okay, I'm really sorry, but it looks like I cannot show the presentation because of technical issues with Zoom.
Vitaly, how about I'll play Andre's update and we can try that.
Yeah, I think yes.
Okay.
Vitaly Bogdanov was having some technical issues, so he will try again in a half an hour. So we're gonna have a brief 25-minute talk on the current progress with the distributed atom space from Andre Luis de Sena, who actually I've been working with since '98 on all sorts of AI systems. Sena was one of the two original developers of the Novamente atom space before it became Opencog atom space, also a lead developer of the WebMind system before that. So like me, he's got incredible patience for banging his head against the same wall over and over and over again. And he's now building the distributed version of the Opencog Hyperon atom space on top of a lot of cool third-party technologies that just didn't exist in our previous attempts, right? Because when we were thinking about how to make the distributed part of Hyperon atom space, I mean, we looked at a lot of options. One was building everything from scratch, and we quickly realized that'll be insane because it's taking dozens of man years to build one of these high-quality NoSQL databases. So Sena will describe how he's managed to get the job done by building sort of custom layers on top of some existing technologies, and early in the path, but we have some working stuff, and then there's a bunch more to be discovered. So, yeah, let's go to Senna's talk. Are you ready? Almost. Yeah, I'm running out of stuff to fill up time. Let's see. What else can I say about Senna? Yeah. He drinks a lot. No, hold on. Yeah. All right.
Hello everyone, my name is André Senna, and I'm very happy to have the opportunity to be here today to talk to you about this interesting project I'm currently working on, the distributed atom space, which is a very important part of Opencog Hyperon. Well, to understand why I say this is an important part of Hyperon,
A little bit for audio right here.
Think we're-
you first need to understand what an atom space is. The atom space is the data structure used by Hyperon to represent and store knowledge. So whenever you have an AI algorithm running in Hyperon, this algorithm will interact with atom space by gathering information and then working this information somehow and eventually creating new information which is put back to the atom space. Okay, you can imagine 2, 3. Hello everyone, my name is André Senna, and I'm very happy to have the opportunity to be here today to talk to you about this interesting project I'm currently working on, the distributed atom space, which is a very important part of Opencog Hyperon. Well, to understand why I say this is an important part of Hyperon, you first need to understand what an atom space is. The atom space is the data structure used by Hyperon to represent and store knowledge. So whenever you have an AI algorithm running in Hyperon, this algorithm will interact with atom space by gathering information and then working this information somehow and eventually creating new information which is put back to the atom space. Okay, you can imagine 2, 3, or more algorithms working together in the same knowledge base, in the same atom space, each of them working asynchronously by gathering information in the atom space and then working this information and then putting back some piece of information, okay, in a way that they cooperate with each other through the information which is shared in this atom space. But in these terms, it's easy to understand that in order to make any interesting stuff in the real world, Opencog Hyperon will need to deal with large amounts of data, either because you need to load a large data set in order to make the algorithms work, or because the algorithms themselves create or build a lot of new information and put it inside the atom space. One way or another, you will end with an atom space with an arbitrarily large amount of knowledge. And at this point, it's important that whatever data structure you are using to store, to keep this information, this structure must be responsive. I mean, it must scale no matter how much information you put inside it. Okay? So we came to the point where we need the distributed atom space, which is an implementation of atom space, which is deployed in a cluster of servers in a way that you can increase arbitrarily the amount of information you put in it, and it will scale well, keeping response time for queries low enough to make AI algorithms viable. Okay? At this point, you may ask, okay, but it's just a large amount of data. Why can't we just use a DB backend to store it like most applications do? Why do we need this distributed atom space as a layer on the top of it? To answer this question, we must pay attention basically to three important points. The knowledge representation, the indexes we use to access this representation, and the cache policies. If you decide to use a DB backend in the backend of Hyperon, the first thing you need to decide is which database engine, which database system will I use. I use a key value one, a graph database, an SQL one. And although this question may seem a simple one, it actually took us a lot of years trying to answer it, and we still don't have a consensus. Okay, why this? Because if you think about knowledge representation, you will notice that some of the aspects of this knowledge representation are better represented in some database system than in others. But other aspects of this knowledge representation is better represented in other DB systems. So you don't have a DB management system which is always best for all the aspects of knowledge representation. And tied with this, we have the indexing offered by each of the DB systems. I mean, it's not just a matter of representing knowledge. You also need to query this knowledge in the database, and you need to do it efficiently. So you must rely on the indexes provided by each database management system. And you need to represent your knowledge thinking about those indexes. Okay, otherwise you will commit the mistake of having a very nice representation, but which can't be properly queried in proper time. Okay. On the other hand, if you are using a layer on the top of this database engine, you can use this layer to represent knowledge. I mean, you may define an API to manipulate knowledge instead of using the DB management system built-in queries directly. I mean, you can have this layer on the top of the DB, and instead of manipulating the knowledge using DB queries, you use an API you build yourself, and this layer will translate from the actions of this API into actual DB queries. And when you do this, we can even use more than one DB engine in the back end. I mean, you can represent your knowledge or some aspects of your knowledge using one DB system and represent other aspects using other DB systems, okay? And then have this layer on the top of the DBs that manipulates only a knowledge manipulation API. And this layer will map from requests to the API to requests of the DB. This is also a best way to use the DB indexes, because instead of planning your knowledge representation having the indexes in mind, again, you can plan only on your API to manipulate knowledge. And then inside this layer, you decide which index of which DB you will use to answer that specific request. Actually, you can even create your own custom indexes and store them in the database itself. It's possible, for example, to have a database engine specifically to store custom indexes you have on your data. And because you have this layer on the top of the database to translate from request from the API to request from the database, this layer will make the decision of which index to use to properly answer each query. Okay. Another important point to keep in mind is the caching policies. The problem with the caching policies of the DBMS we have today is that they use the principle of locality based in time or space in order to make its assumptions. A good cache, what does a good cache do? A good cache will look at the information you are accessing now, and it will try to foresee what information you will need next, in a way that while you are working with the current information, the cache system is fetching the information you need next and have it ready to use when you need it. This is what a good cache system do. Okay? What's the problem with the principle of locality most DB systems use is that it is not driven by contextual locality. I mean, for Opencog Hyperon, an ideal world is that the AI algorithm itself should be able to define what is contextually relevant to me when I'm working with this piece of information. I mean, the same hypergraph being worked by two different agents may see contextual locality differently. I mean, if a given AI algorithm is working with a given piece of information, the information it will need next for some algorithms may differ from others. Okay, so it would be great if the algorithm itself could define to the cache system how it should deal with contextual locality. Unfortunately, this is not possible in most of the DB systems we have nowadays. So having an extra layer on the top of DB storage allow us to implement this sort of cache policy in this layer. So this is the three main reasons we have a layer on the top of DB storage, and this is why we need this, this layer as the distributed atom space. This is the current architecture we have deployed for DAS. And I say current because we are still working on it. So some components may change, or we may also change the way components communicate to each other. But basically, this is what we have right now. So we have a layer of the cache running in the Opencog Hyperon. It's what we call the local cache, which is an atom space fully in RAM, ready to be used by the AI algorithms. And those algorithms interact only with this local cache. They don't interact with the distributed atom space itself. This is done by the local cache. Okay? The local cache communicates with the distributed atom space through gRPC calls using an API, which is a knowledge manipulation API, not a DB querying API. I mean, the calls here are not DB queries. Okay? They are requests to manipulate knowledge information somehow, either to query a pattern, to query something, or to add something. Okay? And then the DAS will translate these requests into DB requests. It will use the AtomDB, which is basically an API for DB access. Okay? Why do we need this layer here? We need it because we don't want to be aware of what DB engines are in the bottom of the back end. Okay? So the distributed atom space use a single API in AtomDB to access database. And this API is responsible for knowing which type of DBs we have in the end of the data of the backend. Okay, so the DAS make requests to this API, and this API will translate it to either one or other DBMS we have in the bottom. So again, the local cache will send requests through the gRPC API to DAS, and then DAS will translate those data manipulation requests into DB requests using this API. And then here, this API is responsible to decide to which DB management system it will redirect each query. Some queries are better answered by the MongoDB, for example. Other queries are better answered by the Redis DB, for example. This is the component that makes this decision. Okay? And as I said, we may have custom indexes stored in the DBMS as well. Okay? Not only actual knowledge information. So to make our proof of concept of this architecture, we implemented almost everything we have here, except the local cache. We run the POC, we obtain the POC results I will show you right now by using Python code running directly in the distributed atom space servers here. Okay? So what we did as proof of concept was we imported portions of the Flybase. By the way, the Flybase is a genomic and genetic database about Drosophila flies. Basically, it is this. And they actually, it is a cooperative work of a lot of research groups, and they made what they call the distributions once each couple of months. And this distribution is basically a very large SQL file and a bunch of additional tables that are not SQL, they are like TSVs or CSVs that are created by custom scripts written by Flybase associates. So it's like every time they are going to make a distribution, they build this SQL file, and then they run a bunch of Perl and Python scripts, and those scripts will process this SQL file and extract and manipulate the information and create other tables that are not in the SQL. They are CSVs and TSVs. And everything is put together in the packet and is made what they call a distribution. Okay, this is what we are reading. But we are not loading all the contents of the Flybase. We are selecting around 246,000 genes. And but for those genes, we are reading all the data from all the SQL tables and a subset of the additional tables which I just mentioned. Okay. Anyway, this SQL data is converted to meta and then imported into a DAS. And the generated atom space have around 2.6 million nodes and 27 million links, which is fairly large for an atom space, by the way. So results, we have this deployment with the most of the Flybase knowledge base available, and this deployment is currently being used by a reserve team to make research to make real research in this data by making pattern matching queries. And in addition to this, we wrote a simple AI algorithm, actually a simple pattern mining algorithm to run in the top of this database. We are not really interested in the results of this pattern matching. This is not part of the reserve research. It's more like we are interested in studying how responsive is the distributed atom space when we have an AI algorithm running with an intense load of pattern match queries. Okay, that's why we did this algorithm, and we measured very promising response time. When we run this pattern mining algorithm, we measured response times averaged below 100 milliseconds, which is quite reasonable for an AI algorithm. And the best of everything, I mean, the best result we achieved is that we didn't load all those data at once. We started by loading a smaller number of genes. We started with a deployment with 2 servers, and then we grew the number of genes we loaded. And to do so, we added more servers to our deployment. So we ended with 5 servers. And what we noticed is that although we grow the number or the size of the knowledge base we're working on, the response time remains basically the same. The average response time for pattern matching queries didn't change when we changed from a deployment of 2 servers to a deployment of 3 servers with the triple of the number of data. Okay, this is a really promising result actually, because it shows us that we may be reaching the point of we can arbitrarily increase the size of the knowledge base we want to deal with in the distributed atom space. So future steps, we have just delivered a proof of concept deployment, which is being actively used by the Reserve research team. And the plan is to have, by the end of this year, an alpha version of DAS with all the pieces in place, which means basically by adding the local cache layer and proper documentation to allow this deployment to be used by other research groups in SNET. Okay, for 24, we are planning to work on improving overall users' experience by having better users documentation and perhaps some specific patterns, specific package for some languages like Python. And we will probably work also in optimization, basically database tuning of each database system we use. Perhaps creating or tuning indexes, perhaps creating our own new custom index from our own. Well, basically optimization and documentation. That's it for 2024. So thank you all for watching my presentation. I really hope you have enjoyed it as much as I enjoyed making it. So that's it. Thank you.
That was great, Andre. Thank you very much. I hope you can hear me.
Yes, I do.
I forgot Andre was recorded. Thinking about the next one already. Vitali appears to be ready, so we're going to pull up Vitali, and then we can go with Nil and Hedra.
Okay. Okay, can you guys see my presentation and hear me?
I can hear you and I can see your presentation.
Okay, thank you very much. Sorry for the technical issues. Fortunately, I have one spare laptop with me, so I just throw the bad way and restocked in the environment. So yeah, what I'm going to talk today is I just would like to have some explanation of meta development roadmap. When I'm saying meta, I actually mean specifically Hyperon experimental GitHub repository we have, and yeah, it is one of meta implementations, as Greg said, and I'm one of the developers. My name is Vitaly Bogdanov. GitHub ID is BOGD. Okay, so what I want to talk about is I would like to make some review of the steps we are going to do in the next year to develop Meta further, Meta and Hyperon. And another topic I would like to cover, maybe a bit more in detail, is minimal meta interpreter, which is a huge part of this, but not the whole activity. Okay. So yeah, first and maybe really step which has been waiting for is alpha release of our interpreter and prototype. And actually, what we need to do to make this alpha release complete is some user experience improvements. So right now we have the code, everyone can get it from the repo, build it and run it and play with it. But there are some things which are definitely not there. So one of things was really developed and delivered just a few days ago, as Alexey already said. It's a custom space API which allows one to develop custom space in Python and then in C language, not only in Rust as it was before. So one thing we would like to improve is a basic REPL and command line interpreter, which one can use to run meta examples. Right now we have one, but it is not as flexible as it could be. And yeah, our goal here is to have something like a Python command line tool, which can be used like a basic code running environment. Then we need to release Python and Rust packages. Actually, releasing Python package which contains a native library. It looks like it is not an easy task, and it's still work in progress. But I hope we will finish it in a few days. And add a lot of documentation. So Rust API is implemented. So our Hyperon experimental prototype is implemented mainly in Rust. It has also C and Python API, and C and Python API are not very well documented, and it is a gap we need to fill. Also, there is a lack of documentation about meta standard library, and what we are going to do is write some meta tutorial and document the meta standard library in a better way. Beyond after alpha release, we are going to make some performance improvements. To do this, we are collecting the use cases, at least some big amount of data like Flybase we can convert to the benchmarks and check our current space implementation, what is bad and what is good about working with a big amount of data in it. And there are some plans to introduce performance improvements. The most obvious is using the current custom space API, developing new optimized spaces. For example, we could develop the space which use type system for indexing atoms inside spaces, parallel searching spaces, integrate with distributed atom space, about which Andrea just told. And also, there is an interesting idea to introduce lazy space querying and transformations to make space API more efficient. So we are going seriously work on it in the nearest few months. Also, there are some usability improvements after the alpha release we would like to apply. Adding the file functional REPL, which I could say as if basic REPL is something like Python 2, fully functional REPL is looks like IPython 2, which has a syntax highlighting after completion of the meta code, add some debugging capabilities, maybe separate debugging or just some debugging API, and implement language server protocol to support using meta from different IDs, not only from the REPL, which is produced by our team. So, and one thing which is core to unblock the further development of the interpreter is we would like to allow more users to participate in the development of the interpreter, but current version is kind of complex. It's a complex piece of code which was wrote step by step, mainly was driven by the user requirements, not by some separate centralized spec, which, for example, Greg was talking about. And yeah, we would like to change it and make interpreter more simple. It's called more editable and allow users other than main developers to look at it and change it, play with it. And what I'm going to explain in few next slides is a minimal meta idea which we would like to implement. Also, to unblock the development for the wider community of people, we would like to make type system more flexible, moderatable, improve import semantics. So last year we have added the importing abilities. As Alexei demonstrated, you can import some external modules in Meta program, even written in Python. But this semantics is not stable and is not very easy to work with, because right now the interpreter has two different sources of atoms. One of them is an atom space. The second one is a tokenizer, which provides some grounded functions. And having both of these parts inside an import introduce some complexities. Also, there is a goal to give a meta programmer more control on inference, like allow control in this direction in better ways than right now it can with current meta implementation. So the minimal meta idea is kind of old idea. Actually, current meta interpreter, as I said, is a huge piece of code, and it's old desire to make this code to make this semantics of the interpreter as small as possible. So to introduce some minimal set of instructions which can be used to build any meta program and even the interpreter itself. So the semantics of the interpreter is complex not because it's like I mean, the complex semantics of the interpreter should not be coded in some compilable language like Rust. It is not necessary. So we can just implement some minimal meta set of instructions, and which is Turing complete, and implement the meta interpreter using this set of instructions. So one of the additional advantages of such approach is ability to represent the program execution path in the meta itself, thus allowing meta code to analyze the execution of some another meta program and keep this execution trace and do the reasoning on it. I would like to explain the minimal meta interpreter in some details. And first, I would like to explain how the interpreter makes the inference on the meta program. So interpreter is probably very similar to what Greg said in his presentation. So the interpreter gets the atom, and basically it tries to find the list of transformation in the atom space. And then each of the transformation comes with some variable bindings, which in atom. So if atom has variables, then variable bindings will be returned with a transformation. And the list of transformations forms the alternatives of the execution of the following execution of the atom. So this list of the alternatives, I will call it plan. It's one big piece of the interpreter context. So on each step, interpreter gets one alternative from the plan and tries to interpret it further. It can lead to the adding new alternatives into the plan or removing some alternatives from the plan. Also, it can lead to the error or some other expected output. So another piece of context of the interpreter is atom space itself. So it's basically very similar to what Greg explained as a tuple of four things. There is atom space is a K, which the piece of this context which was designated as a K in Greg's presentation, and plan is kind of working set, so it was designated by W in Greg's presentation. So interpreter gets one atom from the working set, I repeat, and gets the transformation from the atom space and puts the result into the working set. When the interpreter cannot interpret the atom from the working set further, it just returns it as a result. So which set of instructions can allow us to build such interpreter, to build the interpreter semantics which we need? Actually, we have figure out the minimal set of 5 instructions which can which is Turing complete and can be used to implement any program in meta. So first one is evaluation of atom, which gets an atom, does a search in the atom space, or execute atom if it is a grounded function, and returns result of the execution to the plan. The second one is chain. It is needed to chain different steps of the execution. For example, chain works differently on atoms from the minimal meta instruction set and on atoms which are out of this set. So if atom is out of the set, it just get this atom and replace the variable inside template by this atom, substitutes the variable in template by this atom. If atom is a minimal instruction, is an instruction from the minimal set, then chain executes this instruction and returns another chain where atom is replaced by the result of the execution of the atom. The third instruction is match. It's a kind of conditional operator. It gets to atom and pattern, tries to match them. If they can be matched, it applies the result of match to the then alternative. If it cannot be matched, then it returns the else alternative. Thus, the match is kind of conditional operator for the meta, minimal meta. And last, I have added cons and decons, two functions to construct and deconstruct expression atoms. They added mainly here to make interpreter be able to manipulate by extraction from the meta program and thus construct new expressions or deconstruct expressions and analyze them. It's a basically data manipulation functions or instructions, and actually they can be replaced by instructions to manipulate spaces, or by spaces, or instructions to manipulate by another data. But yeah, here I used the expression manipulation because it's more useful in the terms of the interpreter context. Finally, there are two predefined symbols which are used, which has special meaning in the interpreter. So if some function returns error atom, it means that the execution of the function finished by error, and this error can be preceded by another function and either return it further into the outer context, or just other function can just ignore it and or handle the error properly. And second reserved atom is empty, which allows the user to remove the result from the plan. So if some atom during the interpretation returns the empty symbol, the interpreter then ignores this atom completely and removes it from the execution, from the list of the alternatives. Thus, one can write using empty symbol. One can write the partially defined function, which on some data they return result, and some data they just return empty, which effectively means that they doesn't return result at all. Using this minimal instruction set, we can implement most of the current standard library, meta standard library, which is now implemented mostly in Rust. We can implement it in meta itself. For example, here you can see the example of switch operator, which is implemented using minimal meta instructions. So it gets a list of cases, deconstructs it, and passes it into the switch internal function, which then deconstructs the head into the pattern and template, match the pattern with an atom, and if atom is matched with pattern, then match returns template. Otherwise, it's just make a recursive call to the switch with the tail of the cases. Below, you can see the call of the switch and the result it returns. So it's pretty obvious. Switch gets a pair of A symbol and B variable, and returns that EA because it's matched with the first alternative and don't match with the second one. The at the bottom of the slide, there is a like more real and more useful example from the interpreter implemented using minimal meta. It uses switch to make the type check on the atom, so it gets actual type and expected type, and matches the actual type is expected type and returns atom or empty if no match was found. Another example is a small piece of code which is basically a typeless interpreter of the meta atoms written with a minimal instruction set. So it is a reduce function which gets atom, variable, and template, and its goal to interpret atom as much as possible and then return template where variable is replaced by the result of the interpretation. Here, the function has also makes some handling of the errors. So if evaluation of atom returns error, then error is returned as a result. If evaluation returns empty, then reduction stops, and reduce returns the substitution of the so template with variable substituted by atom. And if and as a third alternative, reduce continues to evaluate the result. So here's a small example with 3 functions which call each other. So foo calls bar and bar calls base, and base just returns the argument, and we can call reduce on foo with some symbol and get the result that symbol is reduced to A. During the reduction, all function was called one by one. One interesting thing which we can do to improve the matching or execution of the meta programs in a minimal meta interpreter is the matching of grounded functions. Right now, the grounded functions execution is a separate piece of code in the interpreter because pure meta functions are executed via querying the space with some pattern and returning the result of this query. But grounded functions are not a part of the this semantics. Interpreter specifically looks for the first atom of the meta expression to find out if it is a grounded function. If it is the grounded function, then it calls it via specific. Then it calls the compiled function or Python function associated with this grounded function atom. And it is inconvenient for several reasons. Actually, some separate execution path in the interpreter means we cannot, for example, use infix notation because interpreter expects the grounded function is the first atom of the expression. It makes us to keep types of the grounded atoms near the grounded function, so in the native code, and it is not it is not possible to get the type of the grounded function using the space query right now in the interpreter. And main disadvantage of this approach is that it makes complexities for the import semantics, because grounded atoms are not part of space, strictly speaking, and thus they should be imported separately. And by making them a part of the spaces, we could make the grounded function execution a part of the space matching. So when the space is queried by the pattern which corresponds to the grounded function signature, then space executes the grounded functions and return results. And for the interpreter, it looks like it is just usual query. So this approach could remove disadvantages we have right now with grounded functions and make them more natural, represented more naturally in the current meta infrastructure. And also, especially, it can simplify the import semantics. Okay, just to review the minimal meta, the properties which minimal meta interpreter has. So execution plan is basically represented as an atom right now, which usually has the out instruction is an instruction from the minimal instruction set, and can be analyzed by human or by program more easily than now. So at the moment, the interpreter plan is represented as a native Rust structure and cannot be easily seen even by the programmer. The execution is predictable because the minimal meta interpreter has only 5 instructions. The semantics is clear, and thus programmer can better predict what happens with this program. This minimal instruction set is Turing complete, and we have an implementation of the Turing machine on it in our repository. Partial functions has a more clear syntax than now. Now we have a no operation, some special function, no, which allows one to write the partial functions, but it is not easy. Sometimes it doesn't work, and it's like one of the consequences of the interpreter complexity. Main interpreter can be written on the top of the basic interpreter using the basic instruction set, and it is the work we are doing right now. So part of the interpreter is ready, but it is not ready. The whole interpreter is not ready, and one of the main advantages of such approach, the type system will not be built into the Rust code, right? Like it is now. So type system could also be implemented in Meta, and also the programmer can write the own module, own atom space, which has some specific type system, for example, which is convenient for his own program, and even write a more convenient interpreter if it makes sense. Okay, so probably this slide basically repeats what I already said. So the expectation of the minimal meta implementation is allow more users to participate in development of the interpreter. I think we can re-implement the most grounded function in pure meta, which is good as well. Make type system more flexible and allow very long awaiting. I mean, the feature which is also not implemented yet, but there is a high demand on it. Make it possible to execute some code during type checks. So we can have type checks with code execution written in meta. Simplify import semantics and unifying grounded atoms and pure atoms representation inside atom space potentially allow us redefining evaluation of the atom inside the program, thus having a better control on the inference direction. Okay. At the end of the talk, I would like to give some more improved functionality features which we would like to also would like to add, but the dates for it's not clear yet. So one of the features which doesn't work, which kind of work right now. So you can customize metaprogram syntax by introducing new grounded functions, grounded tokens, but it is not possible to customize syntax significantly. And it is one of the directions we would like to look at in the future. So another point is that right now we have separate meta execution environment for each platform or language. For example, for Python and Rust, if you are using if you would like to run the Python code from if you are like to embed the meta program into the Python code, it will be the Python standard library which has Python types, and Python part of the standard library will be implemented in Python. For the Rust, it's a Rust environment, and you cannot mix them. So mixed ground functions from different frameworks, different languages, programming languages. It's one of the goals. And there are interesting ideas how to do this, but it's a kind of huge improvement. And parallelized interpreter as well. So basically, as Greg said, probably it was discussed many times. We have a plan with alternative interpretations of atoms, and each of these alternatives can be interpreted further in parallel. Actually, basically, they don't have an intersecting context, and thus they're independent in this sense. So it is one obvious place where parallelization can be done. Another place is, as I already said, parallelizing space queries, and probably, it can be combined with lazy space queries and make even more potential to the parallelization here. But all these features are planned for the end of this year and maybe the next year even, because the specific steps we need to do are not clear yet. That's it from my side. Hopefully I gave you some understanding how we are going to develop the meta and Hyperon interpreter, Hyperon experimental interpreter further. Thank you very much for your attention. And if you have questions, please ask.
Thanks a lot, Vitaly. So we'll have plenty of questions once we start using that software. I guess there's no questions in the room now. Are there questions online? So we're running slightly late in terms of the physical conference schedule in Stockholm. It doesn't matter to everyone online, which is pretty much because of starting late and having an overly long lunch. But this technical content is more important than getting to drinks on time. So I'm psyched to roll ahead. I think take just like a couple minutes bio break if anyone needs to now, and then we will roll into the astounding Dr. Neil Geisweiler on the PLN, and then the Hedra Sayed following up with Neil on PLN. And I think we've seen interesting progress from last year to this year. Last year in the Hyperon workshop, meta interpreter was already working, and we saw some quite limited simple examples, but things were functioning anyway. So now just in the last couple months, Neil and Hedra have managed to get some AI working. It's not that long ago that you got the PLN chainer to work, but we're starting to do some AI in the new system, which is exciting. And I think by next year's AGI conference, wherever that may be, we'll do another Hyperon workshop. And what I'm predicting is that next year, it's going to be a majority AI talks rather than infrastructure talks. And we'll see a bunch of presentations on interesting AI stuff that's been implemented and played within the system. And we're just sort of beginning that transition now after a long period of building out Hyperon system. We're just transitioning to actually using it, which of course will help with the building, because that's what will drive the requirements for ongoing building out. I mean, this is definitely a case of doing research with the system at the same time as doing the engineering of the system, which is always the most fun and most risky way to proceed, right? So Neil, you have a slide deck? Right? Yeah, let's just roll ahead.
I tried to, I don't know, it looks like I'm still in the waiting room or something. So
It's a very large laptop.
okay,
Large
sure.
language model.
Sure.
Yeah.
The microphone is right here.
Okay. Oh, this way. Okay. Should I put this in front of my mouth? Or? 1, 2, 3. That works. Okay. All right. So I guess, yeah. Yeah. So, yeah, I'm going to show our current progress with the PLN port to Hyperon. So we had a version of PLN. So PLN is a reasoning system. It's a logic, but for dealing with uncertainty and to it's a nice logic for common sense reasoning and that sort of things. And we're porting that to Hyperon. So I have okay, let me guess if I share my screen, what's going to happen? So, well, that works. Okay, good. Right. So I'm going to walk you through the code itself, and if you want to follow along, there's actually a Docker image that you can run that contains Hyperon and PLN and a few editors, Emacs, Vim, and Nano. And in the meantime, I'm going to give a little presentation with this funny title, and you're going to understand what it's about. So what's a chainer? Well, okay. Well, let me first recall what's an inference tree or a proof tree. So an inference tree is a way to represent a formal proof. Well, Greg said it. It's called structural operational semantic. This way of representing things as a tree, and in that representation, axioms are leaves. Okay, so we have, for instance, an axiom P. So P would be true, and would have the axiom that P implies Q, and another axiom that Q implies R. And the theorem is at the root of the tree, so that would be R. And we have inference rules, such as here deduction, modus ponens. And okay, that's how we can represent formal proofs. So now the question is, how do we discover these formal proofs? How do we build these formal proofs? And so for that, we use chaining, and two typical ways to chain knowledge to form inference trees is forward chaining. So we start from premises, from axioms, and we just apply rules, and we can generate conclusions. We can generate theorems. So that would be the forward way. So here's an example. So I start with these premises, and okay, here I'm giving away the structure of the tree, but it's just for convenience. It doesn't have to be the case. And I'm just going to apply rules in a forward way. So I'm going to apply deduction to produce P implies R from P implies Q and Q implies R. And then I'm going to apply modus ponens to produce R. Okay, there is the way in reverse, which is backward chaining. So we start from a conclusion. It's a theorem that we would want to demonstrate. And we see if we can go backward to premises, to axioms, essentially, things that are known to be true. And so, okay, here again, I give away the structure, but again, it was just LaTeX coding that didn't get right. Okay, we go backward. So we can go backward by applying modus ponens backward. So we find that, well, if if P is true, which it is because it's an axiom, then we just need to have P implies R, and we would have R. And so we can go backward again with deduction. But there are other forms of chaining that are less considered, but in fact, also very important. So there would be what we could call inward chaining. So let's say if we know where we're starting from, and we know where we're going to, so we know the premises we're starting from, we know the theorem we're going to, but we don't know what's in between. Well, inward chaining would do that. It would just fill the blank. So here it would fill the missing deduction. We could have outward chaining, where we start with something. We know that we're going to use this piece of knowledge in the middle of somewhere, in the middle of the inference tree, and we can just build around it. So we can go backward by applying a deduction, and then we can go forward by applying a modus ponens. And there is, what I call omniword chaining. I don't know if there's a better term for that, but, and so that would be, we're allowed to go in any direction. So let's say I want P implies Q to be part of my inference tree, and I want P implies R, and then, okay, maybe I can go backward to apply deduction backward. I can go forward to apply modus ponens, but here, okay, I could go forward because by unification, I know that R would be the conclusion, but I'm not done yet. Then from there, I need to go backward. So, right, so that's just, I wanted to bring that to your attention, and now I'm ready to make a demo. All right, so, okay, before I do that, I'm gonna give you a little bit of recall various fundamental notions of meta. So, okay, let me, so the first thing I'm going to go over is unification. Maybe I need, do you think I need to change the colors, or is that okay? It's okay? All right. Right, so in meta, right, okay, let me do, all right. I can do once more, all right. Yeah, so in meta, we have a let operator, like in most functional programming languages. But this let operator is actually a fully fledged unifier, and I'm going to show you that. So right, I'm just going to run this piece of code, and maybe I'm going to start by running only the first one. And so here on the left, I've got a pattern with a variable, and on the right, I've got another pattern with another variable, and I want them to get unified. And so that's what let is doing. It's not just filling Y, which, well, is what the let would normally do, but it's also going to fill X. We can see that because if I return link XY, I'm going to get link AB. All right, so you can do all sort of sophisticated unification with that. All right, so I mean, this is just the same thing, but I'm using a special symbol, which is for application, the the arrow symbol for application in for expressing types. Okay, of course it works as well. Whoops. What do we have here? Right, so I mean, this one is just to check whether I can actually run a function in as the how to say, the assigner or whatever the variable that's supposed to write the right variable of the let, and well, it can. I mean, I don't need to do it. We're just getting the same result. Here, what do we have? Right, so here I think it's just to check that it does not. Okay, we don't really care about that. It's not so important. Oh, here we have something else. So the last one, I mean, I'm going to go over that, but already there's a use here of superpose. Wait, there's something weird here. Okay, I'm going to go over that anyway, so I don't need to clarify this at the moment. Now one I think is just to check a way to call functions while doing unification. Okay, so all right, it's just to say that we in fact we have a unifier basically. That's just what I wanted to say. The second thing we have in meta, which is important, is non-determinism. So what is non-determinism? Let me run that thing. So we've got a function here that takes a number and returns a number, but we have two definitions. The first one that says, well, it's going to double the number, and the other one that says it's going to lift it by the power of 2. And okay, and we can run that. Well, now that, all right. And we get two results. We get the one for the power of 2 and one for doubling. So we can run that again, and you will realize that the other doesn't matter. Okay, so it's non-determinism, and like it's really the only semantics that there is, at least at the moment. Right. So okay, maybe I should. So if you want to overwrite, well, I mean, you can overwrite it here in the knowledge base in the code, right? But actually, why there is non-determinism? Well, there are several reasons, but the fact that you can override things is actually one of them, because in the course of defining a function, well, first of all, you might begin with not having a definition at all, only having, for instance, the type signature, and you may, in the course of learning or whatever cognitive process you want to model, you want to run, you might just define, create a definition for that function, and maybe you can create as many candidates as you want. And so that's not something I'm showing, but that's something that's permissible. All right, so just to show you, I mean, we have this superpose keyword here, which is basically equivalent to that. Okay, so the bodies, they are listed and passed to this superpose, well, meta function, and that creates the same non-determinism. Okay, well, you have to look at that. Shows. Okay, but so where non-determinism becomes really interesting is when you have recursion, because then the non-determinism applies to all the recursive calls. So actually you can use that to do, well, very cool stuff. So here's an example, which is just, so we have this bar function, which is actually the combination of a function that just increments a number and a function that calculates the factorial of this number. But if we merge these two functions into one, we don't get just two functions running in parallel and getting us the increment or the factorial. We get the increment, the factorial, and everything that's in between occurring within the interaction of the recursive calls. All right, so that was for the what I wanted to show you before we go to the serious thing. So far so good. All right, great. Okay, so we want a chainer, but in a programming language where types are sufficiently powerful, we know that programs are proofs. And so why not just make a program synthesizer, and then we can reuse this program synthesizer for anything we want, including a chainer. So that's what this prototype attempts to do. So, I mean, I'm just defining a list type in Meta. Why do I need that? I think I apologize. I didn't load the right. Right, that's the one I wanted. Okay. All right, so this is just less than or equal to. We define naturals here. I think it's pretty clear, so I'm not going over that, but if you want me to, I can. These are just functions to go from naturals to number, or vice versa. This is just a function to make it easier to record what's happening. It's not crucial. I don't need to go over that. Again, here, the synthesizer and pretty much the entire code is here. And that's a generic synthesizer. There is one limitation, which is that the synthesizing rules, they need to be binary. Okay, that's there's a limitation here, but it's just because it would make the code simpler and shorter. So it's not an inherent limitation. That's what I want to say. So what do we have? Okay, let's go over the type signature. So we have a function that takes a query under the form of an atom. It's going to take a depth. That's going to be the depth of the program we're trying to synthesize, the maximum depth. Here's going to be a a knowledge base, or you can think of it as a set of constants or a set of axioms. Here we have inference rules, or rules used to synthesize things, to combine things. And here is just what it's going to return. So let's go over the first case. Well, so we have a query here. We have a def. We have an axiom, but actually this axiom is non-deterministic. So this thing is actually all the axioms that are available. We have a rule, but again, this rule can be non-deterministic. So it can be all the rules that are available. And all we're trying to do is we are trying to unify the query and one of the axioms. And so the weird thing is that this case, so you see here, we have a def, but it doesn't involve the def. It's because the def means not the exact def, but up to that def. So that thing can actually be seen as the base case of our of the underlying recursion that would build all the programs. And here we have the recursive case where we have, well, again, our query. S of k indicates that we want our def to be at least 1 because it's recursive. We have our axiom, which in fact is a non-deterministic, and rule, which is non-deterministic. And what we're trying to do again is we're just doing unification. So we start by unifying a rule with a special format here, which is actually saying, well, I want my rule constructor or my rule name to be such, and I want the rule type to be such. And here you've seen I've used the term premise and premise 1 and premise 2 in conclusion, because this thing is in fact is representing the inference rule, but it's represented as at the type level. This colon operator is a way to represent that this thing is of that type. So it's going to be clear when I'm going to show you examples. And the rest is just unifications again. So here we have a query, and we're going to deconstruct the query into well, the application of that rule. But to apply it, we need a proof. We need a proof of the premise of premise 1, and we need a proof of premise 2. And what is a proof? Well, it's a program. So here, what this thing says is that this thing is going to be the program or the proof of that thing, of the conclusion. And here we have the recursive calls, where we are going to just call synthesize over, well, the queries that this has to be the proof of premise 1, and this has to be the proof of premise 2. And that's all. And so now we have an example. As knowledge base, we have a set of functions. And as rule base, we have ways to combine these functions. So we have two rules. We have the regular function composition rule, where basically we take two unary functions and we just stick the output of one into the input of the other. And here we have, well, it's the same kind of a composition operator, but it's a little bit more sophisticated. And so we can run this synthesizer.
So let me run the first. All right, so okay, let me just well, yeah, I prefer to actually run this thing. Yeah, I'll have more room if I want. All right, so let me rerun that. Okay. Right, so the results. So I've called the synthesizer over this query, which is just find me any term, any program that is the type of any type, but with depth 0. So it's just going to output the constants and their types. All right, so let me find something more interesting. All right, so let's run this one. So it's the same thing, however, so it's the same thing, but this time the type is completely specified. And so, well, we want the program that has this type. And it finds it because we said we only want to have depth 0. All right, so where do I have? Okay, so that would be an example where we have depth 1. So wait. So here we want to find all the programs with this type signature, string to number. But we're allowing to make right one composition at most. And so while the synthesizer found this program. All right, so we've got program synthesis right here. But we've got more than that. We can do, for instance, we can do type checking, right? Because here I'm just gonna ask, well, wait, I need to make sure that it's correct. So I'm gonna ask, oh my God, what are we doing? Right. Right. So here the query is completely specified. So program is specified, the type is specified. However, if we get something wrong, we won't get the result. We'll get nothing. So if I replace number by bool here, I'm not going to get anything. Well, okay, I'm getting something, but basically something that wasn't able to. I mean, Meta was not able to reduce this thing. It was blocked, and so meaning that it failed, meaning it failed to type check. But we can do even better than that. We can do type inference. So that's correct. Right, so it was able to infer, so we gave that as fully specified, but we didn't give the type as fully specified. And so the synthesizer just went in that direction to infer the type. All right, but we can do even better than that. We can do all kind of chaining. So let me try to find one. Well, I need something that's gonna maybe, yeah, that's not bad. So here I have a query where the program is not fully specified, but we know we want to use H, which you could view as being an axiom, a premise. And we want the type to be partially specified. So it's neither forward, well, it's kind of a, well, it's kind of a forward chaining query, but the conclusion is also somewhat specified. So it's kind of a mixture of forward and backward chaining. We can do that. Well, it's going to take a little while, and we've got a lot of stuff here. But whoa. Oh, I think I gave you, oh, no answer. All right, this one didn't. Okay, well, it wasn't supposed to give an answer, so that's why. All right. This one is supposed to give the answer, but you get the idea by now. And right, so yeah, here we got something. Please, why it's not doing what I wanted to do. Oh, no answer either. Okay, well, all right. I picked again the wrong one. But in any case, you get the idea. So now I can move on to the PLN port. And so I don't know how much time I've got left. So don't know how. All right, so okay. So we're just using the same thing. It's just that the axioms and the rules are different. So here we have a deduction rule. So here we have the name of the rule, the constructor, corresponding to, well, the corresponding data type that corresponds to the rule according to the Curry-Howard correspondence. And here we have the rule itself. So here we have the premises. Okay, so okay, let me just walk you through quickly. Yeah, walk you through that. So what this thing expresses is P. Well, think of P as a, I mean, think of P as an event, and think of PTV as a sophisticated probability measuring measuring the prevalence of that event. Except it's a bit more than that, but I don't need to explain that for this presentation. So that's going to be enough. And so it basically says, well, if I know the probability of P and Q and R, and I know the conditional probability of Q knowing P and R knowing Q, then I can infer the conditional probability of R knowing P using a formula. And that formula is just meta code. It's just a function that's gonna calculate probabilities given the probabilities of in the premises, and that's it. I mean, that's a PLN rule. And so how do we use that PLN rule? Well, in the same manner that we use the synthesizer, but it's just it's just different rules. And whoops. So here's an example where we have our axioms, which are going to be, well, some measures over P, Q, and R, and some measures over P implies Q and Q implies R. And our rule base is just this single rule, the deduction rule that I've just shown. And we're going to be able to produce, I really have to change the, let me find something better, because I don't think that's very readable. Right, that's better. Right, it's going to produce this inference tree. And so how it's going to do that? Well, we're just going to call the synthesizer. We're going to call this the synthesizer over this query, meaning I want to prove that P implies R, and I want the synthesizer to complete the theorem with the truth value. And I also want the synthesizer to find me the proof. And so we can do that. All right. So I hope it worked. Come on. Yes. Oh, read on. Okay. All right. So let me just paste the result here. All right, it's here. The answer is here. And so here we have our sophisticated probability, which is a truth value, and which is here fully defined by the formula. So we can just do the same, but we can combine multiple rules to be a more sophisticated inference trees. So that would be an example here. So we have a rule that would take, that would basically take observations and build a kind of approximate how much, say, P implies Q, or the condition, approximate the conditional probability of Q knowing P given these observations. And I don't need to go in detail over that, but basically, let's just say that we define our rules. We have one here, we have another one here, which is just to cast some truth value type into another truth value type. And we can call that. So we've got our knowledge base, which here says that just, well, P of 42 is true and Q of 42 is false. And so we want to find how much P implies Q based on that. We have other things. It's kind of sophisticated because when you start to take into account evidence, you don't want to double count evidence and so on. So that's why we're already dealing with some kind of a set theory here, but I don't need to go over that, I think. And oh, this one only is involving one rule. I mean, I'm going to jump straight to a demo involving two rules. So, right. So here's a more sophisticated example where we have evidence, and we also have, well, we can say we have direct evidence of what these predicates are doing, and we have also indirect evidence, such as we indirectly know that Q implies R to some degree. And so we can just put all that together and reason about, for instance, how much P should implies R. So we're gonna synthesize this tree, and I'm gonna jump straight to the right. So yes, I can call this one. It's gonna work. All right, it's calling both, but all right, this one. Okay, let me. Don't think it should take very long, but maybe my laptop is in a power save mode. I don't know. Well, I mean, anyways, I hope you get the idea. Do you have any question at this point? Yep. Oh, well, yeah.
I will ask again.
So, yeah.
Have you tried this operation on a set of equations?
Right. So the answer is no, but it's definitely possible to do. I mean, as long as you have algebraic laws about how you should manipulate the equations, yeah, totally doable. Pardon me? Well, I mean, this thing, it should in principle handle any mathematical object. So the answer is yes, it should work. Now, well, I mean, it's a Hyperon is a still, you know, a work in progress. So are we going to discover bugs along the way? Yes, it's possible. But if it does not work, it's because there's bug that needs to be fixed. It's not a, it wouldn't be an intrinsic limitation of the system.
Following up on that, I was wondering, have you played around with truth values being probability amplitudes as opposed to probabilities? So using complex numbers and.
Oh, well, the answer is no. But again, I mean, we could try. So I mean, the two numbers we have. I mean, if we're getting into that, these are well, I don't think they have anything to do with amplitude, but they actually represent a distribution, a second order distribution. I mean, I think you could say they represent a second order Bernoulli distribution, which is usually a beta distribution. And I mean, you could use just you know, alpha and beta, but we use here a strength that would be a proxy for a probability, and here a confidence. Yeah.
Yeah, quick comment on that question. So on the level of the PLN mathematics, I can't remember if I published this anywhere. I think I may have somewhere or other, but I mean, most of the basic PLN math simply works if you're dealing with complex truth values, because I mean the first order PLN is pretty much Bayes' rule, which has a perfectly fine analogy in the quantum matrices, and PLN deduction formula. I mean, you can formulate that in the probability distribution form. It's just matrix multiplication on distribution. So I mean, you can do that on amplitude distributions just fine. So that the PLN, like on certain truth value math, works fine on quantum truth values, and there's no particular reason why the control mechanisms would be dramatically different. So you could do that. I mean, we don't have quantum computing hardware that would let us efficiently do quantum PLN at the moment. Actually, on Monday at the AGI hardware workshop, we'll have a quantum computing guy from Gothenburg come down, so we can chat with him about that actually. But so the other thing I noted, so while the strength, confidence, truth values, they're not the same as quantum truth values. One thing I found is if instead of strength, confidence, you reformulate as positive evidence, negative evidence, which is similar to components, just shuffling things around. If you take those positive evidence, negative evidence, truth values, and you stretch them by a certain nonlinear function, you can make it arbitrarily closely approximate quantum truth values, but not quite get there. So there's a sort of approximate mapping between the positive evidence, negative evidence, and then the real and complex components, but it doesn't ever get quite exactly the same, which has to do with the different algebras of the two in the end. Like basically conjunction and disjunction are okay, but negation of the quantum truth values comes out not the same as negation of the positive negative evidence truth values. And you know, quantum knot is weird, right? So that's there. You could do PLM with either one, or with much weirder, with octonion truth values, or whatever you feel like, right? But what's the purpose becomes a different question. If you had quantum hardware, there'd be a big purpose, right? I mean, then you'd have like a quantum atom space, and you could have metacode like driving the quantum atom space for certain purposes, which will be quite interesting.
Any other questions? It hasn't started yet because everybody's still going in their rooms, but there is a reception afterwards. Yes. Yes. Thank you very, very much, Nell.
All right.
Ben, did you want to introduce Hedra?
Next speaker is Hedra Said, who's a senior AI developer in SingularityNET, and I think now is playing a lead technology role in Rejuve Biotech as well, working on applying our AI in the bioinformatics domain. So Hedra started out in our Addis Ababa office in ICOG Labs, then moved to the US some time ago. Has been working for us from there. She spent a while working in Opencog, building some parts of the Opencog pattern monitor, then shifted for a while to working on AI for bioinformatics, and now she's back digging deep into Opencog, but it should be a convenient synergy, because one of the things we're looking at doing with PLN and Hyperon is biological inference. So she sort of got both sides of this here. So we'll turn over to Hedra for the final talk of the day.
Thank you, Ben. Hello, everyone. I will go ahead and share my screen. I hope you can see it.
It's coming through beautifully and we can hear you perfectly.
Sure. So I have this example, usage of Meta. I will go ahead and walk you through the algorithm first. I'm trying to implement the pattern miner using Meta. I think you can see my screen, right?
Yes, it's coming through very nicely.
So I will go ahead through the algorithmic sketch just to give you a head start, like what I'm doing. So the pattern miner algorithm we have is of these 6 steps. We can start with any pattern in the atom space, or a given pattern in the atom space, which is our starting point. And the second step would be getting the evaluation set of that pattern over the entire set of instances inside the atom space. And we can create the shallow abstraction of those valuation sets, where we can specify the value of each variables, the possible instances, and then we can we specialize a pattern by composing it with the elements of the shallow abstraction, and then we do count the instance of those specialized patterns. That's what we mean by enough support. So at least there is a minimum support that we need to look for each instance to be called specialized or to be counted as a candidate pattern. And then we will repeat this step again and again until the termination point. So let's say this is just an Opencog classic example. Let's say we have a pattern, which is an inheritance link, which will match, which will get matched to the, let's say if we have an entire atom space and we have such a pattern as a initialized pattern, so that will get matched to all of the inheritance links inside the atom space. So once we have that, the valuation set extraction will be collecting the value of each element of the inheritance link, the X value and the Y value. So once we get that, we can determine the shallow abstraction of the x and the y, meaning that possible value of possible value of x and possible value of y will get collected, and then we do the specialization. So the pattern we started with is an inheritance link. So the specialization will be, we will carry out like a put in this operation in the Opencog Classic. In our case, it might be considered as the late operation, so that we can unify by using the valuation sets. We do the substitution or the beta reduce for each of the values. When we do that, let's say if we are reducing or substituting the value of the variable x, we will keep the value of y untouched, and then the same will go for the other variables that we have. So once we have that, that means we will be having a specialized form of the pattern we have for each possible value, so or instance inside the atom space. So then once we have those specializations, we will go ahead and calculate the support, which means counting the number of instances inside the atom space for each specialized pattern. Then once we get that, we can do many things, like we can stop there and replay or give the surprising patterns just by doing the stuff like the first iteration, or we can go ahead and do more things like combination. For example, we can combine different specialized patterns which have at least the minimum support count or the number of instances inside the atom space, and do calculate the surprisingness of those patterns. Let's say by combination we can combine such a pattern, like X can be linked to some relationship, and it can also be linked to the other relationship, and we can combine and do the counting or the support. So I am trying to implement the same thing with meta. So let me show you this. So I have this example from the Opencog Classic again, which says, which have a couple of men and women who are soda drinkers. So some of them are linked or mentioned as ugly. So we need to find such surprising pattern from this knowledge base. And to do so, I have loaded the atom space over here. As you may see, I used like the knowledge representation is exactly the same, like the atom is representation, and it doesn't matter in meta. So I will go ahead and load it. And once I load it, I do have some libraries and parameters to use and the helper function that I will go over. So what I did is then the 6 steps that I mentioned earlier will be done like step by step. So the baseline we need to have as a baseline, at least we need to have the valuation set and the specialization of the pattern we start with. So for this demonstration, I used an inheritance link as my top pattern, or just to start with. So once I have the pattern to start with to search, so I can collect the X values and the Y values, which means the valuation set, using pattern matching. As you may see, I'm matching an inheritance link of XY and getting the X and the Y values and assigning those values to X and Y variable. As Neil mentioned, I'm here using the late operator so that I can be able to use the unifier. And I also use a non-determinism of meta. So I use superpose the reason for that is I have this specialization of the pattern where I keep the X bar untouched and replace the value of Y in the let operator. And I also keep the Y variable untouched and replace the X value from the let operator. So once I get this, A will be my specialized pattern. So all of the specialized patterns will be collected with A. So once I get those specialized patterns, I will go ahead and calculate the support. And when I do calculate the support, I do have a minimum support threshold. And if the count I get from, which is the number of instances I have for specifically the pattern I have from A or the specialized pattern I have, if the number of counts, for instance, inside the atom space is greater than the minimum support, then I would go ahead and take that pattern as a candidate. So otherwise, I would do nothing. So by the end of this step, I will have every possible pattern which have at least the minimum support inside the atom space. So this is a baseline. We can continue doing this, but once we get this, the next step I will show you is combination. Like I can combine those patterns and get the support of those combined patterns. Let me show you this one. So at this step, what I'm running is I'm just running the baseline, which is finding every possible candidates inside the atom space. And as you may see, I have a bunch of results. Let's say I have, one of the candidates is X being a human, and I have 20 count for that. And the other is X being a soda drinker, and I have 10 counts for that. And the same will be for other instances as well. Let's say concept node Lily, which is one of the humans listed inside the atom space. It has he or she being something has a count of 3. So I will collect such candidates first and do the composition or combination. But when I do the combination, like as you may see, this is just using the baseline. I can go ahead and do the combination as many times as I want. So like an n-gram, I can combine twice, 3 times. I think the maximum is 3 in this case, just to do not suffer from the combinatory issues. So I do have a combination of 2 patterns at a time. So in this case, I also use the non-determinism like as a way of forming a combination. So if I combine the same pattern twice, which it's considered a list, or it's considered non-determinismly, it has multiple values. So I will get a combination of every element inside those lists or those superpose. So that way I do the combination and do the calculation. So it might take a while, but I can show you the results over here. So I get every candidate pairs can be paired twice, like in the second iteration. Let's say I will say X is a woman and X is ugly. I will have 5 candidates for that. And X is a woman and X is a human. I will get that. And the same goes to the ternary, which is combining 3 patterns at a time. Then I will say X is a human and X is a soda drinker, as well as X is ugly. and then I will get the same thing. Like I will have 5 counts for that. So once I get this, the idea is I will calculate the surprisingness of each candidate pattern so that I will get the top candidate, which is the surprising candidate pattern, which I will give as a result. So to do that, I have a simple surprisingness formula here. I just re-implemented the Opencog classic one. I haven't used the complex one just to demo, for the demo purpose. So yeah, I can show you a bit for the example I have. So doing so, the surprisingness for the candidate pattern X being a human and X being a soda drinker, I get 0.6, where I get the surprisingness of X being a human and X being a soda drinker to be 0.3, because being a man is more specific than being a woman, a human, right? So yeah, so that way I can filter out my results down, and I also get the 3 combinations or 2 combinations at a time. So let's say X is a human and X is a concept node, the soda drinker, then X is also ugly. I will also get the same result with that of a human and a man, because I now have 3 combinations. So this way I calculate the surprisingness. It's a work in progress. I haven't done most of it, but yeah, it's something that I can use Meta for. Like I use Meta to do such a thing. Yeah, I think that would be it. There are a few things that I consider while doing this, like some of the combination patterns might not be strongly connected. So I have to deal with some of the things, but I'm not done with the filtering of non-strongly connected components. But the idea is, if let's say, for example, I have a combination of patterns which are X is a man, but also some other concept node or some other knowledge is something else. So if I have if I consider such a pattern, then I have to filter out such a pattern because it's not strongly connected. So I don't need to consider such. Okay, so I have done some extra work to get the variables of combined patterns, but other than that, I think it will be it. Yeah. If you have any questions, maybe.
It was awesome. Thank you very much, Hedra. Any questions from the room? Or Alexei, did you want to ask your question and get clarification?
Well, no, I guess it's okay. So my question was, is there some live output or everything was in comments pre-computed?
Oh yeah, there is a live output, but it takes 2 or 3 minutes to run. That's why I haven't run it. I only ran the first iteration. Yeah. I actually wanted to use DAS just as a query language. Like I can send it's actually the counting, which is taking much time at the moment. So if I were able to use DAS, that's the idea, which I haven't done yet. So if I use DAS, then I will just send the query of the pattern matching to DAS and get the counting of those instances. Like, yeah, that would actually help. working especially with larger atom space like the bioatom space and so.
Yeah, so the comment I wanted to add is that so yeah, so the goal, what Hedra is trying to do is to basically so port the pattern miner of Opencog Classic to Hyperon. But so she's using this code, which is in pure meta, which is by itself is pretty nice. But her goal is then to go from that code to using, well, the DAS for well, handling very large atom spaces, and also the synthesizer, and then to mix that with PLN.
Yeah.
That's right.
Yeah, I forgot to mention the synthesizer. Yes, yeah, that's the next step.
Yeah. So I had two questions, and Hedra already answered one of them, which was about looking in distributed atom space, which is where most of the bioatom space will need to be kept. And of course, distributed atom space has its own caching. So then the things that are used frequently, maybe in RAM within distributed atom space. Yeah. The other thing I wanted to ask was precisely about the PLN and pattern mining used together, because I remember in pattern mining in Opencog Classic, we often hit questions where you hit cases where you didn't just want to mine patterns, but you wanted to sort of scan the atom space, and then you're looking for things that match a template, maybe after a little bit of inference has been done, right? So the thing doesn't necessarily match the pattern exactly, but after a few short steps of inference, it will match that pattern, right? And we were just starting to look at stuff like that in Opencog Classic. I wonder, are there particular advantages or peculiarities to doing that in Meta and Hyperon, or is it just porting? That may be a question for either Nil or Hedra, or for the future.
Yeah, that's for the future.
Okay, but we're not too far from playing with that now, I guess. Yeah.
Yeah, I think we can take advantage of meta being like the chain. I mean, the program synthesizer that Neil showed will be much better use in pattern miner as well. Like we can actually do the pattern miner, most of the tasks of pattern miner using the program synthesizer. Yeah.
So you're asking the program synthesizer to synthesize basically new subgraphs that match the pattern, and then in order to do that, it has to basically do the pattern mining. But how does the control mechanism differ from the classic pattern miner when you're doing it in the program synthesizer, though?
In terms of control mechanism, it should be unified by just controlling the interpreter, because the interpreter, as of right now, the interpreter just goes like exhausts all the possible branches, and that's not what we want. We want to direct the interpreter and to prune the tree, the branches of the non-deterministic interpretation, and so how do we do that? I think the idea of how to do that, well, first it should be completely user programmable, so we don't need to. I mean, we could do it or AI meta. Right, I mean, of course, completely programmable. But what we can port from Opencog Classic is just the same way that you can, say, control an agent in a virtual environment, while you can just use the same methodology to control an inference or controlling an interpreter, right, over a program. Yeah.
So yeah, I wanted to make a final comment on just the use of these bioinformatics and bioinference problems. I think there's a bunch of advantages for us to using these examples because a bunch of us are quite familiar with it. We have large structured knowledge bases of relevant information that you can fill up a large atom space with, like fly-based and gene ontology, strings, pathway database. There's a whole like bioatom space we've curated, and there's a lot of nicely structured text like PubMed abstracts, which we're now working on translating into logic form, and we have actual real research problems we want to solve here, right? Like we have genomics from long-lived flies. We want to figure out their implications for human beings. So there's real problems. There's a bunch of real data, combination of structured data, text data, and quantitative and genomic data. The downside of this application is kind of nobody but us understands what the hell we're talking about, right? So I think the same things that we're doing on this bio AI use case, we want to develop on other sort of similar use cases that are easier for people to understand. Some of that's going to happen in the true AGI project, which is a sort of Opencog Hyperon for business project, where we're going to be doing similar things with different sorts of databases. But I think for now, the bio AI use case does sort of have everything. Like there's applications for every aspect of proto AGI stuff we want to play with in Hyperon. It's going to be quite interesting to see where it goes. And yeah, any more questions for Nil or Hedra on PLN or pattern mining? Or I guess any more questions for anyone, since this is the end of the workshop? All right. Alrighty then. Well, thanks everyone for thanks Hedra for the outstanding
Thank you.
talk. And Nil, and thanks everyone for surviving through the day. So I think, as I said in my introduction, we're at a super interesting time with Hyperon development. As you've seen the last couple talks, we're at a point where we're now able to start doing some AI in the new system. Just barely, but it's going to be more and more and more over the coming months. We'll be doing more AI in the system concurrently with building out more and more of the infrastructure for greater scalability with the minimal meta interpreter, the meta to Rolang compiler, and distributed atom space, all sort of rapidly maturing while we build out this AI in the system, both Hyperon internal stuff like PLN and pattern mining, and then the bridging of Hyperon and other systems like LLMs as well. And so I'm giving a 15-minute talk, I think, on Sunday, which is on Galois connections. And I mean, I can't say much in 15 minutes on that, but then I think Nil and Hedra are doing talks on stuff related to these two presentations, but a little more theoretical and less hands-on demo-ish, I guess, but more on the program synthesis and so forth. Also Sunday afternoon, then Monday in the AGI hardware workshop, I will talk about the putting Opencog pattern matching on a chip. Rachel St. Clair will talk about her hypervector chip, which can also be used to manipulate hypervector embeddings of atoms in atom space. And then Andy and Manhin, I guess, will have a presentation on the current sort of prototype experiments for using LLMs to map English into Opencog logic formalisms. We've got a few more bits and pieces of Hyperon stuff during the rest of the conference, and I may be missing something if Alexei is giving a talk too, which I don't remember. But we can look on the program.
No,
Is he? What did he say?
I don't have a talk.
You don't. All right. Well, I can hallucinate your talk like ChatGPT. It'll be even better than the real thing. So yeah, thanks a lot, everyone. And for anyone who's listening online and not already engaged with the Hyperon project, feel free to join us. I mean, there's Opencog Google group, and there's a Discord group. There's a True AGI Telegram group. So and there's GitHub, of course. So we're available via multiple media outlets. So please join. We're trying to build the world's first thinking machine, do it right in multiple senses, and we could use all the help we could get. Thanks a lot.